the presentation?
Yeah, no
Okay.
problem.
And I can see your slides fine, and your audio is good. So we'll start in 8 minutes.
All right.
Okay, why don't we get started? Our next speaker is Dr. Yoon Miyawaki. Did I pronounce that correctly?
Yeah, personally, not Yoon, but June.
June. Okay, thank you.
Yeah.
Um, and is from the National Institutes for Quantum Science and Technology in Japan. And is going to talk to us about the ultra high resolution two-dimensional RICs at the nanoterasu beamline 02002U.
Yeah.
Thank you.
Uh,
You can begin
yeah.
anytime you're ready.
Okay. So yeah, for stable connection, please there up. So there's a downloaded video there. Okay. Thank you for the kind yeah introduction. And I'm Jim Miyawaki from there is a QSD Japan. It is Nanotelas is a new synchrotron radiation facility in Japan. This actually it started a ring operation last year, last April 2024. Then we spent about 1 year for commissioning the beamline and there, yeah, this spectrometer. Yeah, we successfully achieved this ultra high resolution for this, yeah, spectrometer. And yeah, honestly, I was a bit surprised when I saw the timetable that I have 90 minutes also to maybe yeah this title sounds just too specialized for weeks, but I try to broaden the topics for this long presentation. Okay, then so the we just started the user application from this year. So from this sector, we just started the scientific case. So the main part is the design and development, and the performance of this spectrum of optics approach. Okay, right. Yeah, this is outline of my code. Yeah, I'd like to do with the last part to the introduction. First, I'd like to talk about the nanotelastics. Especially this nanotelastics was constructed a bit in some complex way in the sense of the budget. Not only from the budget, not only from the national government. The budget was from the industries. Third is I'd like to give you some framework on this one. And our next one is the risks. This is especially the subject lesions, not the hardware place. And then third part this is in the subject leak, achieving the ultra high resolution was so demanding in our community. But it is very difficult and there was a lot of challenges. So I like it to mention this as challenges. Then as you can see here, there's the at 930 eV. This is a kappa LH. Actually, we made it that this is just elastic scattering from the multi, so that directly reflect the total energy resolution, including the beamline spectrometer. And then we got the 16 millieV, and then in E over delta E, that is nearly 60,000. This was the this is the world record. Okay, so to achieve this one, there's a yeah, there it is that we employed the unique optics 2D rigs, we call this. So that it is I like to show the that features. Then it is I like to talk about the color performance. And in the last part, this is my interest to this magnetic materials. So it is using this ultra high resolution and CD circular dipole. Yeah, we successfully identified the magnet's polarity. So that I like to briefly show that this our side case, and then in the our side was nice. Okay, okay. Before they are selected, there all the members when developed this beamline. This is all the member of the QSD's beamline group, and then especially the code A is there. Also, there's a beamline side. So this beamline is here, and one of the design phases which is there. got a lot of advices these purposes. And in the last part, why this sample was from the Tohoku University. Okay, and okay, this is an introduction about the nanotest. In Japan, actually there are 10 single facilities, including this nanotest. And now this is the newest one, the 10th one. Maybe this is Springate is famous. This is one of the biggest one. It is but in Japan it is including the very small one. Actually, it is older is I believe this is the smallest one in the world. Also, not only from not the only public one, it's the private one. Yeah, this is actually the private one at the university. Then yeah, this is now there's the 10th one. This is this is the campus of the Tohoku University. And you can see there is a ring here. Maybe this is all the common in the world that the synchronization facility is far from the city, but and that is the case for Springate. Springate is very far from the city. But the Nanoters is very near to their city. There, yeah, in this Tohoku area, one of the central station is the Sendai, and out here, I believe that there is a subway station. So the between subway station and that's Sendai Central Station, and it's only 10 minutes. And from this station, it's only the 50-minute walk. The bike car is only 5 minutes. So that is this facility is very convenient for this is coming from even from the Tokyo. And that is the announcement has started operation last year, April. And this is a very complex framework. It is how we constructed this one in sense for the target device. Then maybe this translation from Japanese political is not easy to understand, but we call it public part, private, the regional the partnership. This public sector is national government, and the government, the government designated this our institute QSD for implementing the agency. So then this private companies and also the local regional government equal partner. Then it is that representative. This is POSIC. This is and also this is the local government. This is the Miyagi Prefecture, the city. Also, it included university. Then the budget is roughly half from this national government, the 20 billion yen for accelerator and the 30 lines, and it's roughly half or 18 million Japanese yen is from this air department. So this is not the national government. This is a private company, and it is I'm a beamline scientist, so this they're kind of working with this public beamline. So this is basically for this academic use and open to the user. This is the way this proposal forms. But this 7 beamlines. This is mainly for industry. So to use this beamline, the industry, the private company has to be a member of this coalition. They're investing this it is a certain amount of money. And if the company wants to become a member, then the company can get the 10-year membership, and each year the company can get the $2,000 beam time. Then this is but not only you're pay for the money to be a per membership, they needed to pay this certain amount of money to use the beam time. That is the profit to this contract. So like this nanotellus it's in the budget part is heavily weighted the construction. Okay, Yeah, this is this. Yeah, I go to the scientific part. This is a storage link monitor nanotels. Yeah, you can see this one, and this yeah, like this. There is a lineup, and then here the link, and this is the main parameter link. The beam energy is 3 Gallic volt, and the lattice structure is double the bin from so this the emittance is below 1.1 millimeter radian, and the our second fluorescence here, yeah, this is 350, so relatively small one, yeah, middle size, and basically all these parameters were already is realized except for the beam column. So then actually it is there from the initial operation, it is the beam column was limited below 200 milliamperes for stable operation. But in this summer shutdown, an accelerator team just upgraded the link. Then it is from there after the grade. This September is beam column has been gradually increasing. So now it is 360 milliampere, and next week they will increase to 400 milliampere. That is the final target.
Mhm.
And these parameters will be realized. Okay, this is the performance of the nanotellus photon flux in the deliriums. In Japan, this is the very big this instances like our is spring rate, but so that is now are comparing this nanotellus and the spring rate, and the spring rate is planned to operate the spring rate. The yeah, if you look at this photon flux, yeah, this the red one, and then the suffix lesion is higher even though the spring rate 2 case, there is green one and blue. And also the standard plate is roughly this one can to this seven composed. Then the flux your display one is higher, and also the brilliance is better than it is but the hard explosion is yeah the spring rate is superior. So that in Japan this is these two this has two different purposes. So this is basically the spring rate is for hard explosion, and the nanotellus is a suffix lay and relatively low Alex. So they sort of tender regions. And in the first phase or the construction of the beamlines in nanotellus, there is a 10 beamlines were constructed. Yeah, like this. And there's a total the beamline is we can construct 28. So the 14 for undulated, 14 for regular beamlines. This can give us the like a beamline is white beam. And yeah, this blue one, this is the public beamline. And this red one, red one, and this is for a coalition beamline. This is basically for the industry. Then, okay, so this is the so let me address this BLW. This is my beamline for ultra high resolution reefs. And the second one is BL60. This is AfPS beamline. It is especially for this micro focus or nano focus. And the future plan is also include the spin resolved ones. And the third one is BL13. Sorry, 13U. This is basically for the absorption beamline. This is very this beamline, this IV is very special node. This is a common one. So this can give us the very fast switching. So yeah, this is a summary of the specification is for this B9 L2U, L6U, AfLS, and 13U for XAF. And yeah, because of ID, this is the BL2 and the 6U. This is something common one, Apple 2 type Android, but our targeting laser region is different. The BL2 is a relatively higher, so 250 to 2000. The other six is the version is 50 to that 1080. And this BL13 is the segmented uplander. So this is the in the long ID section. It is the ID is divided into four parts. And then also then in these IDs, imaging IDs, there are three gaps, and then there phase shifters are installed. So we're changing the phase between the IDs. There's yeah, this can change their full control of polarization is there. Of course, it can give you linear, vertical, horizontal, circular, also the elliptical, and then any arbitral angle that is familiar with linear polarization. And then in the feature is using this phase shifter. The switching frequency is will be there's more than faster than 10 count. And then is this is the beamline part that is there. There's for the each purpose. So there's the on the kilometer is different. Here, yeah, employ a different one. Yeah, OBL30 to achieve the ultra high resolution. We use their focusing time VLS. Then it would translate. But the OBL06U and 13U is there. Split this. And then the OBL06U. This midline is the imaging or this focusing is important. So the collimated one is that, yeah, and this can allow us to change the size at the exit plate. And we have continued. This is kind of the common one is long fields on type. And yeah, the BS13U is you're using this special one, and the inner lane is very wide, so that from 180 to 3000 it is covering is the lower part of the 10 line. And yeah, resolving ports is LPU. This aims for this very high one, and also the VLZ6 of this series is try to get it is high resolution, but it's low energy. Then it is the absolute delta E. You can use 1 millimeter with this at 50 V with 50,000 resolving both. And 13U, this is an XAS beamline, so it's not so high resolution required. This is the latest is 10,000 in the orders Okay, there's the focusing size is here, the 06 series is there. Now we have the only beamline. It's around this several micrometers. And it is there. Now we're constructing the egg range, and this will try to achieve nanometers and 100 nanometer. Okay. Okay. So this is just showed this fraction about the ELZO6U. This is for the AfPS beamline. And this is a two branches. One is A branch for non-AfPS. This is still under construction. And the B branch it is for micrometer size AfPS. Here it is the we get the energy resolution in the 60,000 and 65 eV. So there's the energy resolution delta E is around 1 millieV. And now this size is 5 micrometer, 10 micrometer horizontal vertical. And yeah, this debug is already open to the user. Then there's some first scientific results, or it is already obtained. And this is the for the dimension area dependence, or the YD0 is the kind of the Q point, ITCC. Right? Okay, this is beamline view for the status, and this yeah, this beamline can give the wide range of electron positions. Lower one is I don't know, 180 for all KS. Then is the highest one is here 3000, and this is there. Then we can have the root ruthenium LS like this. And our display line can also our focus being here it is a several micrometer size. So this by scanning the sample, and we can get this kind of this MCD image. This is the domain of the sunlight material. This bright spot. This is their this red one. This is the dark spot. This blue one. This meaning that the spin orientation is opposite. Yeah, by using it is there some test pattern is there special weather is around 2.4 is also 2 to 3 micrometer. Like this is Yeah, this one is we can already measure this their conventional axis. No. We're now developing the polarity switching using the segmented this, andulators. And this during this conversation, and it's more or less we are came to the final stage. So from next year, from 2026, we can open the using the OLED switch to users. Okay, this is a just wait already. Yeah, during the construction, so this is aerial view of this Nanotella site. One it is 2019 is April, and it is you can see this the very just flat land, and using our over 1 year since they're accelerated. Yeah, maybe you can see there's maybe there are some big uh, this is bowling machine. This is accelerated to get the very stable and robust floor for the accelerators and beamlines. Then the over 3,000 pillars, columns are digged around here. Then there's roughly 10 meter to reach. There is a very stable. There's a rocks layer. You can see that this brown one is the sand. So this is the soil is not so solid. We needed to reach the stable rock state. So it took about 1 year. Then and then the 2020. So this is there is a building construction started. Then in roughly 1 year, this is we got the building. Then they we started constructing the accelerator, beam, and also the beamline. It's mainly to the 2022 and 2023. Okay, uh, this is the introduction of what is the rigs and this 2D rigs. Okay, before it's looking at the rigs. Rigs is a resonant inelastic X-ray scattering, but it's before they're going to the rigs, it's non-resonant. So it's just inelastic scattering. So I'd like to talk about this one. Actually, this concept of this technique is very simple. Here is the sample, and then if you hit the instant X-rays, sample is then due to the interaction between the sample and instant X-rays, then it is some or it is their state in the sample is excited. Then the scattered emitted X-ray is that energy becomes slightly lower than the instant X-ray. So by comparing the instant X-ray energy and the scattered X-ray energy, we can notice there is some excited, there is some energy level in the sample. And also, not only the energy, you can see here it is a momentum, which is because X-ray has the also momentum. So it is a purple one, and it is yellow one, and this is then they're just there in this configuration. There, this X-ray gives the momentum. This green momentum to the sample. So by changing this yellow version, this yellow one, we can change there is the momentum transfer to the sample. So by measuring this angle dependence or the rigs, we can know this the dispersion or this some or the elementary excitation. So just like AfPS. In the case of AfPS, we can know this boundary dispersion. It is okay. Then this is if you use a resonance, then the resonance is using the kind of XCS. So this is a schematic or this energy level of this materials. There is a core level state and a balance state and a production state. And then it is if you tune the instant energy to this this energy separation here, then there is the sample that absorbs this photons like this. So here in this intermediate excited state there is a core hole and the excited. Their core hole state is very unstable. So it is very fast. It decays the electrons like this, and then with this decay, is photon is emitted, scattered. So using the resonance, we can just drastically increase the cross section. This is there. It is important for software systems. And okay, this using this resonance, X-rays carrying into the feature all leaks is like this. It is the here. So first one is to this resonance. There is this method technique uses element and the chemical selectivity. This is by selecting it is the energy in the X-ray absorption spectroscopy, and same as X-ray absorption, and we can use polarization dependence. And the third one, fourth one, and fifth one is the comparison with the photoelectron method. It's this rigs here uses we call photonian photon rods. So it is we detect photon. So it is compared with detecting the electron. This technique is bulk sensitive, but also we don't need the conductivity. So we can measure not only metal but an insulator, and our sample environment is more flexible. So it is not only solid, it is we can apply this liquid and gas, and also sort of photon out. This photon is not only affected by this the electric field or magnetic field. So we can measure this with this one. So this is very suitable for the Octarand experiment. And the last one is this is a kind of comparison with neutron scattering, inelastic neutron scattering. INS, inelastic neutron scattering is one of the very powerful technique to measure photons and magnons. But this neutron requires a large sample, several millimeter size, and a thick sample. We call the cross section is very, very long. But those X-light is this. They can focus, and then also the cross section is large. So we can use a very small sample, and also the thin field. Yeah, this is good point. But actually, there's a soft X-light rigs as very severe the fundamental limitation. This rigs process is very much photon handling. Yeah, meaning that the sigma is very low. So to achieve this ultra high resolution, we needed to compensate this very low measurement throughput. Okay, this is a kind of demonstration of our element selectivity. This is a perfect element selectivity. This is an example, or is a myoglobin. This stores oxygen in our body's muscle tissues. This is the 1,500 atoms in one train. But here is ion atoms. There is only one single ion atoms here, but are in big using the resonance. If we tune their energy to these ions, then it is we can measure it from we can from 2p state to 3D state, so that we can only notice only about these ions electrons. So if you compare this infrared, the visible light pulse, and the ultraviolet UVs, here it is. Here gives us just a whole electron state, but the rigs is the perfect selectivity. And this is also necessary introduction is the versatility of these rigs. Yeah, rigs can be applied to not only solid, we can apply the liquids or the gases, and also there are some functional materials like battery, cathodes or anodes. And in the case of solid, this is a very familiar or this main physical topics is to explore the electron states, like ITC, superconducting plates, or semiconductor analysis, multiplex, or any quantum mechanics. Then the rigs can give the coarse particles. This is orbital's yeah, this is from orbital and magnums from spin. And a phonon, this is solid. And then this with a resolution is now you can reach the 20 to 30 milliliters, and then we can get this kind of dispersion of phonons. This is and yeah, this is for key plane. This is with in this case the electron phone coupling and in the and in the case of liquid, this is the result already. That's the water. And actually, liquid water has there two different structures. One is like ice, and one is like gas. So that state can be it is distinguished from these two things. So it is so using these two things for the identification, all it is structural. This the liquid is there a lot of the solutions are was measured and the thought well, this is for gases and gas is the is isolated to the atoms or molecules. So if you measure the gas or the dilute, then they're small, but you can see the similar peaks. This is the progression in this molecules population. So this is directly connected to this potential surface like this. So by measuring this one, so we can get this potential surface. That gives us the knowledge about how the molecules are the molecules surrounded by any other circumstances. And for the materials, this also very to give the personally this very technical it is a results for the cathode is in the lithium ion batteries there is not only is there metal but the oxide is oxygen that's is incorporate the charge compensation and that was clarified that the district is so that in oxide it is all two but here they claim that it's using weeks. It is there it is by charging the discharging, and then O2 minus is just molecular O2. So this is something there's balance C is bottom zero. So that is a very huge charge compensation. And this is the key for this inclusion in the lithium ion battery. Okay, and this is also the demonstration of the interaction is there. Rigs is the measurement tempo element. This is very flexible. So this suffix lakes, we use suffix basically when it is the they need to measure this bond in vacuum. So it is there. This is photon out take. Sorry, this is are using this kind of the differential pumping system. Because we can measure this even near the atmospheric pressure ambient pressure, there's a zero, it is just atmospheric pressure. And this one is a leaky cell to measure the leaky solution. This here you can see that actually it comes the both side. And then here there is a very thin window. It's only this there passes through the X-rays. Then it's hit the solution into here. And then the emitted X-light is through this thin film and then to the spectrometer. And by using this kind of cell, we can measure the leakage. And then there's also this applied leaky cell. We can measure this current experiment for fuel cells, lithium ion batteries. Here like this for this this window is evaporated is there. There's the cathode and all materials. Then there's adding there some is counter electrodes. Then it is this part there's a real helium button. So that we can measure this it is to this operand distribution. And also here it is there. Yeah, this is plotting and photon line. So there's with the magnetic field, there is no effect to the instant in the scalar X-ray. So like this, we can measure the rigs with under the magnetic field. Okay, so all right, then it is what kind of elementary excitation is the rigs can measure is here. Is that the rigs can almost hold the equilibrium, charge, orbital, spin, and lattice. And each corresponding lattice there is given the photon, and charge gives just charge excitation and some dB excitation. There's orbital gives dB excitation, and the spin gives the magnons. And these are the equilibrium. It's this is from the Takula's paper. Then there, here that you can see spin, charge, orbital lattice, and also there is a topology. Here it is, or it is intelligently connected. And finally, it gives the register functions that is like topological like the computing, ultralights, or magnetics. So it is knowing how these equilibrium behaves in the solid. We can know this physical properties, so the mechanism or the physical properties in the solid, and the rigs can measure all these particles. So it is in that sense, rigs is very powerful tool. But really there was a problem. You can see that in this scale, the photon is dealt to 50 milliliter nanometers. There's the 100 milliliter, and to separate it is two here the photon piece, magnet piece, which is comparable or a better energy resolution. But it is not easy. So our community, it is Rick's community, it is the in these 10 to 20 years, we developed there's a higher intelligence machine. Is the first epoch making one is there's the address at the six light source. This first for the first time reached is the resolving power of 10,000. There, the 10,000 corresponds to the roughly 100 MeV resolution and at 1,000 MeV. Then after that, the AfLS, or this is after the upgrade, so it just reached 20,000, and that diamond light also it reached 30,000, and at six and an NSL in the United States, it reached the 40,000. Then there's the last one, it gives 22 MeV at the AfLS. So there is the here in Japan, it is the we aim the lowest one. This year, the number of the parentheses is their target. Is evaluated, is we set at 100,000. And then in principle, we get the 10 millib resolution, and that's 1,000 millib. Then, but now it is finally we got the 60 here, 60,000. This is much better than this one. Okay, so just that golden power is not easy to understand. So if you look at it, this one. So this is the same sample, but the different interval resolution. Before the 2000, and the resolution is nearly 1 dB. So that you can see this is just one the broad P. And then if you those also become less than 1, and then you can see that some elastic and dB excitation. And then the resolution is there less than 0.5 dB. So that here is the elastic. Maybe here we can distinguish that maybe there's not only the one elastic, but here is some inelastic component. And finally, it's there at SLS. It reached nearly 100 millib. And in the clear, you can see the two different peaks here. So like this, the resolution is very powerful to distinguish these very small peaks. Then after this, they tried to show this the forms of the by different sample is in at ESL. They're using the 35 millib. There is a very small features here, and at United States 622 millib, and in our spectrometer 2D we accept AfPS, which is 60 milli. Okay, that is how much good resolution that we need. It is of course from the scientists, but the better resolution is better resolution they requires. But the one the number is this thermal energy scale is that room temperature is corresponds to 30 MeV. And you know that like the superconductors is that the physical properties is appears in low temperature. Of course, this thermal energy scale is at low temperature. The blood is the physical property. So to distinguish it as a low temperature physics, we need better compatible better than this one. So for example, at 37 dB, this is the nickel we can use the photons and magnons. And at 25 dB, this is for molecules, but yeah, we can see very clear this the vibrational progressions. So are getting the higher resolutions. This is there. Then we can plot this lower energies. Then we can distinguish discuss the mechanism versus there is materialized properties. Okay, but there it is achieving a ultra-intelligence is not easy. It's very much a challenge, especially for the software play, because software is very it's very photo-angly. Here, this slide explains how. Okay, this is a sample. Another day is an X-ray. The X-ray hits the sample, but the emission probability is very low. It's roughly 0.1%, 1% or 1% of this suffix layer. So then that emitted X-ray, scatter X-ray, is not one direction, it goes into all the directions. But the spectrometer can collect this very, very small here. Small there's angles. And to achieve there's a good resolution. The display then is for the energy distortion in the spectrometer. That the efficiency is not so high. So the total throughput, we can calculate like this. So the throughput is 1 times 10. So if you can get instant flux or is 1 to 12, so this is a lot with the high value. This is for suffix light. Is even using this very high photoflux, there it is there. The count of the detector is only 100 photons per second. So this is not enough. So usually it takes 30 minutes, 1 hour if there's a photon counting the count of the detector is such a low. And actually, if we go to higher resolution, is this count becomes much lower. Okay, then why is subject lyrics is technically very difficult, but why would you try to measure the subject lyrics is here? The subject region is there's a very important low Z elements case is our carbon, nitrogen, oxygen, and also the LH or 3D metals, and the MH is 4F metals here, and this kit and also LH and an MH. This this stage is quite electron is excited directly to the 3D for this is valence electrons. If you consider think about the AfLS case, there is a example from 3D metal is it excited electron is not go to 3D, it's 3P. So this is in some sense we get the indirect information of the valence which directly determines their physical properties. So the software plays are very important to discuss. There is these functions in the material. So this is we try to we're making very big efforts to achieve the software plays. Okay, but okay, this is the just the comparison of the feed use the conventional technique. If we try to get the 10 dB resolution. How much is the throughput? Okay, so this is just look at this relative throughput models. This is the one is the best resolution spectrometer at AfLS in the United States. Then the total net resolution of beamline the spectrometers. And the design value is like 90, 30, and 15, 14 dB. Then the relative throughput, you can see that if we were make 1/3 of this resolution from roughly 90 to 30, then the relative throughput comes less than 10. And also there's if we are reduced from 30 to 14, so roughly it's half the resolution, the throughput. Again, this becomes less than 1/10. So it is if you go to 14 to 10 dB, again, is the throughput becomes 1/10. Actually, this isn't just a relative throughput. The case of this ultra high case, we need several hours to get 1 week spectrum. So it is their throughput becomes 1/10. That means the win is maybe 20, 30, 40 hours. So there's 1 day or 2 days, and it's impractical. So achieving this energy resolution level, we're going to use the conventional technique or optics. So we need to think about something new one. So that is the 2D mix. Because like the just. Okay, this is a bit easy slide. It is there, but not just BL2 is ultra high resolution rings facility. Then it is there also the design, and it is there the performance. So you can see that this procedures and these papers. And the point is there, this beamline is very long one, 76 meters, and this spectrometer is also very big one, 12 meters. So using this, they're a long beamline, and big spectrometers will achieve the resolution, 10 millib, but that is not enough. If we use there is monochromatic X-ray, then as I told you, the throughput is too low. So from here, this is the monochromator. So it is from this gradient, and there we get the dispersed X-ray, energy dispersed X-ray, and there is no X-ray sorted to the sample directly, energy dispersed X-ray is radiated. So using that one is we can the drastically increase the throughput. And you can here see the difference between the conventional beamline and the AfLS. Here is the molecular meter, and usually we have exit slits here. So by using the very narrow slit, and we pick up the molecular magnetic X-ray here. Then there's molecular X-rays, they are radiated to the sample. Then as a whole, is analyzed using this spectrometer. But in the case of the 2 leaks and all gas, it is used as this bus X-ray from molecular meter. Here, this sample is placed here, this exit slit portion. So we need some special optics. Because if you analyze this emitted X as a whole, it is in due to this portion or lens and resolution becomes very bad, worse. That mechanism is 2D X. So it is using this side view. So it is a perpendicular plane, and there's a top view. It is the horizontal plane. Using this perpendicular, this is vertical one, horizontal. So using the vertical plane and the horizontal plane in the perpendicular planes, we implemented 2 different functions in this side view. This is perpendicular plane. Using this water imaging mirror. Here, this gradient is colored represents the energy dispersion from the beamline. Here, this portion can be imaged like this, and in the perpendicular plane and in the horizontal one, this is a kind of a common set all of the spectrometers and is emitted scatter X-ray, whereas it is dispersed by the lights. So in the spectrometer is detector one direction here. the horizontal one is the scattered X-ray, and the vertical portion corresponds to the portion of the sample. That is the energy difference. So in the conventional ones, we only get just this one slice of the rig. But in the case of 2 weeks, with a lot of the slices or rig spectra, then it is the spice as having the whole spectra of the weekend is the address includes the throughput. Okay, that estimation is here. Yeah, again, it is there. It is the 6 case. It is there. If you're design at 14 millib, then it is if you're design at 10 millib, like this, the conventional one throughput is 1/10. But if we use this 2D rigs of this, here is there if the design value said we said that 10 millib, the throughput because better than this conventional one. So that means there is these 2D rigs to get one speaker well it is roughly 7 hours. This is practical. Okay. This is the photograph of my beamline. This is a very long beamline. It is here you can see the molecular data. Below there is optical hatch and there are 2 mirrors, the first mirror, second mirror, and then this white one is optical hatch. This outside of the optical hatch there is an entrance light, 2 entrances for vertical one and the horizontal one, and this is molecular meter. Here is there able to plane meter and the gradings here. Yeah, you can see this is the inside of it. Yeah, here you can see the 3 gradings. And now we install the 2 gradings. One is that then in the future probably we install is maybe higher silver or higher energy one. Okay, this is the overview of the spectrometer. Yeah, like this, and then this is the inside of the this our sample chamber. Here this is the incident X-ray. There is a M3 in here. This is refocusing there. This only the focus is the horizontal direction, and here there is a sample and an emitted scanner X-ray. It's there imaged by this endpoint, and in between this sample chamber and detector, there is a grading for the spectrometer like this. Again, there are 3 slots, and it is now the whistle the 2 and 1 is static. Okay, this is just the movie how this works. Here to do their angle is all the rigs. This very big one, it is 20 meter. It can be rotated like this. Okay. So now this is it is flight is in 30 times faster. So from the edge it takes around 40 minutes. Right. And this is also the kind of break. Here you can see the BLZ2U. This here it is. Here this is a ring. So here is the ID, and this line here represents the beamline, and this fan shape is their spectrometers, and then which must flow through 30 degree and 150 degree. So when it is big space, and accelerators there. During the construction of this building, we found that the space is not enough. So it is we needed to expand. So here you can see there is some extra space here. This is to accommodate the expand shape where the floor is expanded, and also you can see this square. This is the pillar to support the seating of this building. But in the first design, so there was one pillar around here. But if there is a peer here, then we can also select this one. So the ask is the R is calculated is please year change there is like this. Finally, this is there. And yeah, we can this is this very big beamline and then this spectrum. So it is probably this yeah so there's what are the construct in the building. So it's very important that the do this in this big size. Okay, and this is a key feature of the optical design. It is this is a kind of a common topic or to achieve the high performance in the software plane. For example, the high resolution that is very small in the focusing side, good imaging, and then the first one is there to get a good resolution using the grading. Accelerator is that to achieve this higher resolution simply when it is there very more yeah more dense. The higher it is glue density gliding. So, for example, in the case of ESLF, this first one is for beamline. The second one is uh, for spectrometer. Like this is to achieve the higher resolution when it is nearly the 2000 line per millimeter. And here in the spectrometer, we need nearly 3000 line per millimeter. But here, other theories are by using this second order or the third orders, we can reduce the gloom density. So in the beamline, using the second order, yeah, okay, sorry, skip this is a diffraction plate. So the diffraction, there is a diffraction order for the first one, second one, third one. So here is the second order. We can use this is the are the goodness half. And then if we use the third order, we can make it goodness 1/3. But usually it is in a laminar gradient, and if we use a higher order, then the glue diffraction of the efficiency becomes low. But we optimize the graze angle it is in the graze is gradient, even when using higher orders. There's a black one in its first order. That is their energy line is relatively wide, with the peak diffraction efficiency lower. And if you go to the red one, the second order, the range becomes narrower, but the peak efficiency becomes higher. And if you go to the, I don't know, I get that's there, the range becomes much narrower, but this is the peak diffraction efficiency higher. So using this higher diffraction orders, we're successful in to make the glue density lowered. This is important to manufacture the blade. Basically, this lower blade is easier to manufacture, so then we can get better quality one. And yeah, this is their photo blocks and then the beamline, and this is their the calculation. It is there. This is their IDs photo blocks, and then the photo blocks or the yeah that the second of the gradient, and then if we compare it to the ESL results, where we use the second order, but it's polymer order is better than the ESL event. So it is the second order using the second order, the third order. It is one choice to achieve the higher resolution. And this is there talk about how to image the this is the incident dispersed X line. Is we use this water mirror. Water mirror is composed of this hyperbola mirror and elliptical mirror. The combination of these two mirrors. And this is a combination of two. So the parameters are all yeah. These are this is this not single and so that we needed to optimize the uh, some criteria. So that if only it is aimed for the imaging, it's very simple. But it is in the case of a speculator, we need both the throughput and the imaging quality. So this is gives there this, information about here by changing the theta. So this corresponds to the incident angle. There is a volta there. If it goes to the glazing instance, then there it is there the acceptance angle, the collecting angle becomes lower. But if you go to the go to the normal instance direction, then the acceptance angle becomes lower. But in the X-ray region, is there refractivity very addressable is becomes lower so at the higher incident angle. So that is the we need to think of both the acceptance angle and the reflectivity. Then finally we get the effective acceptance angle and the some pair parameters that we get the maximum one. But this is all just there it is acceptance angle. If we think about the imaging property, we need to think about the field of view. Yeah, how a big region is this North America Canada image without aberration. This is one example. It is like this. This is source major tree that is they are magnified and an image here, and then the center part is there is clear, but then if it goes outside, it becomes large due to the aberration. So how much region looking at this image with operation, there is one parameters. For example, in this parameter, here it is there almost no operation, but if you go outside here, then that's the image size become larger or black. So this is this using this shape that we can get there. Yeah, in this case, roughly plus minus 60 micrometer. The region is almost no aberration, and that field of view was also calculated is there. So if you go to there, normal instance, there is the field of it becomes higher, but the acceptance angle becomes lower. The final figure mainly to look like this, and then we can there's optimize the display the just like this. And then this is for the 900 dB, but if you calculate the lower energy, 250 and higher 2000 dB, like this is the depending on how large, how wide energy lane is we use. We need to optimize these parameters. And then finally, also there's if there is this watermelon is a kick down, there's the accelerator, there's the lambda level, so that kick down is too large. This detector comes near to the floor level. So that is there. Also think about that balance. We here chose is 5 here, so that we can measure even at the highest energy 2000. And using that simulation, it is this is the almost this 2 weeks. This is the simulated elastic scattering position in the detector, and then it becomes like this tilted, and then in the center it's narrower. This go outside, it becomes it's a bit lower, and in the simulation, it is it includes the spectrometer spatial resolution, and also shifted there, along the selection, and then we can get this image. So this is what should be clear. Let's clear that. The center part, it's it would is narrow, but if you go outside, so the exact resolution is like this. So the center part resolution is good. But it goes outside, and the resolution becomes worse. So in our spectrometers, on the detector, plus minus 4 millimeter. This corresponds on the sample. It's plus minus 100 micrometer. So we can get the good imaging properties. And the third one, there is the to achieve the good resolution is for the energy resolution or this imaging resolution. We need good stability. For the ultra high resolution energy resolution, with their incredibly high stability for gradient, like in 30 non-radiant in the beamline, and there's in the spectrum thing that 13 non-radiant is this is very much challenging. And this to achieve this one is through the aerial bureau the building. It is mentioned that we just put there very yeah a lot of pillars slabs to the blocks. They the stability and the robust lower usually. Okay, so there's here this area I showed is there the performance of the two rigs. There in reality we achieved. First, that is I'm sure that there the focusing size at the sample. Here, this the there's a photon source, and then in the by the first mirror we focus vertically here in the 10 micrometer. This is here horizontal, so it's 126 micrometer. Then this they are horizontal side, firstly focus what is M3 voltmeter to the sample. Then finally we get the horizontal sides are all roughly 0.7 and 0.8 micron, less than micrometers along the horizontal direction. And in the vertical direction, that is the energy dispersal direction. So like this simulation is are here. Horizontal direction is both sides is some 1 micrometer, and it's along the vertical direction is it is there it is dispersed one. So this very big one. So to the sample, this kind of line shape are X-ray is already. And this is the first phase or the energy resolution optimization. Usually it is for the beamline, and then we measure the hydrogen absorption like this. And that lifetime width is 110 PdV. So it is measuring this one and the fit him. But it's with the Gaussian, and so we can estimate the energy resolution. But our interest collected this lifetime with this has 100 millimeter. So it is difficult to estimate the less than 20 millimeter. So like this is by changing the parameters of the molecular meter. That's called CFF. Then we can make the change there. The resolution is it's gradually becomes better. At some point, the estimated there is calculated value from this method and satellite. This is due to uh, the limitation of this intrinsic lifetime of this. So what did it do? I think of the different way to optimize the beamlines and also the spectrometers resolution. Then, yeah, we are actually using the elastic scattering. Oh, there's the sample. This includes the both beamline and the spectrometers resolution. So, by optimizing this waters, that is the TLI, that is the beamline CFM spectrometers, then finally we can reach the best resolution. So this is when it optimizes the beamline, the spectrum becomes high. Then we optimize the spectrometers. There it is beamline becomes higher. So okay, so this is the very first result. Is the last summer. Is after the 3-4 months commissioning, we obtained these resolutions. For the 930 EV, this is kappa LS. This is the benchmark energy for this soft electronics community. And we have two resolutions. One is high resolution, and the other is ultra high resolution. And in the ultra high resolution mode, this is we go to 60.1 BDV. This corresponds to the U model, and is here is 60,000. This is around this. And it's like this is using only the 3-4 months we achieved the this resolution. That is I think this is it's very short the commissioning time. Usually it is small time. So this is, I'm proud of this results. And after this, sorry, this is before the improvement. This is I like to do the throughput. The 12 weeks is and it is achieved both ultra high resolution and the high throughput. This is a comparison with AfPS. This is a Taiwan photo source. So this is also one of the very high throughput spectrometer. And then we compare it with this blue one from TPS, and then this is another test one. What it is compared to this one is their ring pilot for the 200 milliampere. So it is we double it is with time. But it is you can see that these statistics in more or less stable. Again, over here it's a bit better. So like this is the throughput is yeah. Uh, also high. It is the typical it is there in the case where this recurrent 200 millimeter, it needs 20 to 30 minutes for high resolution mode, the full 2 hours for ultra high resolution. And now you got it. Well, you can 400. So let's call it this time you can start. Okay. Uh, this is just the it is how we analyze the resulting data. So it is in this detector we didn't apply the centroid. Of course, it is a pixel size are all the this detector is a 60 micrometer. And the spatial resolution is not gained out to get the ultra high resolution. It is weighted less than 5 micrometer. But in the soft light detectors, there is no such small pixels one. And also there are the spread function is sort of the in order to there make the pixel size small, it is there in the real and the spatial resolution it is not comparable with the pixel size. So this is the we need a center. Central is there. This if the one photo gets the pixel, then it is there. That charge cloud is not only needed one pixel, but it needs spread to the next neighboring pixel. So by this calculating the spread, we can uh, get the better result, spatial resolution less than the one pixel. To achieve that, we need single photon event modes. So usually we set the exposure 1 second or really less. So that we need to, if we wanted to measure 20 minutes, yeah, we set 1200,000. Then we measure the 20 minutes. So in one shot, it's very so intensive, but it is analyze this what it is. We can add we can get better resolution. And but I think this one is like this. We can see the I tilted. Then after this, we shift this one to this yeah this horizontal. Then integrating along this motion, and we can get this kind of spectrum. But in reality, yeah, this is a very ideal case for it. It's a very flat sample. But in the real sample, yeah, it is this line is not smooth like this. Here it is jump and also support. There's no signal, but there's a to analyze this one. We need to align this like this. So it is using the yeah this method is we implemented this one is so this is in the first phase it was difficult to measure this kind of real world very rough sample or not sample but now uh we can measure it in the real world. Okay, then it's the resolution that I showed was last year as well, but after that is there was still it is trying to make the results better and better. And finally, yeah, this blue line. This is for high resolution. This right, that right is for ultra high resolution. This design volume. So in high resolution, what it is, we reached the best one is it's compatible with the uh, design volume. So like that oxygen gas in high resolution mode, we can reach less than 10 milli. And you use the ultra high resolution here, then we can get the less than 7 millimeters. This is our O2 gas or the vibrational permissions. It's very, very sharp. And but the problem is in the ultra high resolution mode. And this is the design value, but we cannot reach this one. Luckily, it's not in line. It is the our target is the coastline. If coastline the real quality of the gliding, then it's luckily we can reach this one. But still, we need to optimize. But it is at the present, this one is which is optimized. It's 710 dB. This is iron LS. And then we got 7.1 dB. This corresponds to the resolving power of 100,000. This is there. Influences are on this dream or this is reaching the 100,000. But this, we're still it is trying to make okay. This is a demonstration design. This is how there's resolution with a resolution change in the shape or in the spectrum. This was measured at spring 8. It's about 10 years old one, so the resolution was 150 millib. And this is SLS lights, Swiss lights also. So the resolution was 45 to 50 millib. Here it is, the resolution is much better. And it is there, yeah, this is width in the graph is the same with only this one. So if it reaches 6.7 millib, it becomes this is very sharp. And actually, this one was upgraded and the Hornets was upgraded transferred to the AfLS. Its resolution was improved from 150 to 50 millib. So this is also has this with the very versatile. It is some environment for ligand cell. This is also is very powerful. Is competitive machine is that. Okay, and also there's using this imaging properties, we can measure the microscopy. There's a spectral microscopy, like so. We're using this imaging mirror. We can use it to check that this type edge is resolution is this. So that in the center, all is the resolution is good, so it is very sharp. But it is if you go outside, the resolution gets worse than as expected by this simulation. So this is there in the present setup. There's the best resolution in the center is 1 by kilometer. So the width of this is exactly that the horizontal is 1 by kilometer. The best resolution along the vertical is 1 by kilometer. So now we can measure this there 1 by kilometer is the square size microscopic spectrometers. And this is so the demonstration is the log micro analysis is like this. This is made of nickel film. And this is measuring this there. This one is along the one-dimensional scale, and we got yeah this signal. So this yeah you see that here it is. This line is Nolan is all the calculators are left later to 2 micrometers. So we can easily distinguish the 2 micrometer. And if we apply this technique to the real sample, we can PS. So it is the one of our materials. It's very thin, but it is to get the thing for the we use exfoliated method. So in a real sample, here yeah this gold or yellow part is bulk thickness, and it is this blue one is there relatively low thickness, and this yeah blue this part is roughly the similar monolayers part. So what are the measure? Yeah, who wanted to measure this sample? It is we need to know it is exactly this part, and then we use our 2D rigs, the microscopy technique, because we can easily get this shape. So that is yeah. In case for this very thin part is too weak to get the intensity, but it's There are local to this output, the port. We can identify the target portion. So they're after getting this image, they said that this line, we can measure this portion. Yeah, to get this image, it takes only 1 hour. So for this kind of a very small sample, it is our spectrometer is very powerful. Okay, the last part is this are the first scientific case that is we move into the wire. This is a very typical. There's the spintronic materials, and now there's the chirality is like key topics in it. Is there the physical properties and here this is a quote. This is the chiral structure. That the chiral structure was identified as the chiral photons. And result three, there's ultraviolet. This also gives there's a color magnets. There's a magnetellite and the club are some culprits try to distinguish that hierarchy. This is using the RIX MCD, but unfortunately the energy literature was not good enough to distinguish the separation in the two different Kylar magnets. So this is as a demonstration is we measured the YRZ two different or 80 kyloid angles. These YRZs are fairly magnetic one. And so in acoustic one, here you can see here it is here from the total view of this left direction is there the accelerator. And this the optical mode is there the rotation is opposite. So that so in the YRZ, that energy separation is the 20 millimeters large enough. So, and for demonstration, if we use our ultra high level spectrometer, we can separate these two, and then demonstrate is there, and the RIX CD or MCD can distinguish there's different polarity. So yeah, okay, this is not RIX. This is a polarized neutron scattering. It clearly shows that there's a different polarity here. So would like to show the thermal using the rigs. And then yeah, we first made the rigs, not rigs, but this is just MCD or XAS. And then we got this one, this because the fires in the fair magnet. This they are opposite the spin moment. It was orders like this. And we set different two energies like this. Then we got here, yeah, this one 710.5 maybe. Like this, it is a red one is higher, but in the 711.1 maybe the blue one is higher. So like this is the for the different opposite spin states that we got. They are opposite to exceed. So this the analytical response to yeah, it's blue and red now, and it's a neutron scattering. So using the RIX and CD, we demonstrated that this kind of industries identified in this quality for the first time. And because this portion of the we measured like this, actually in this kind of 3D material that was measuring this portion is not easy, and this was also this during our development. And unfortunately, it is the finally we could measure this portion like this. Okay, or the simulator is there. We developed a new expected at nanometers years old. It's now operational and developed users. We achieved ultra high resolution as well this one, and demonstrated that it's capable for also the RIX microscopy using the 1D imaging. And then there's a key application in the shown there's identification of all the fundamental priority in the virus here. So then we show the opposite chiralities in the acoustic optical values. So this is we build that this first so with a RIXIM CD can probably from the chirality or virality. There, thank you for your attention.
Oh, thank you. This is was a tour de force, a very impressive beamline. Are there any questions for the speaker? I have a couple actually. But
Yeah.
let me ask the one that's most on my mind, and that is the you have the sort of the detector assembly sort of on this cantilever that rotates around, right? But it looks like it goes from, let's say, 0 to 60 degrees. Doesn't do an entire 360-degree rotation. Is that right?
Uh, uh, you mean there's there in the movie?
Yeah. Well, and then in the beam
Yeah,
line, in sort of the floor plan of the beam line shows that it just sweeps maybe what, 30 degrees or maybe 45 degrees.
R is this is a rotation angle is from 30 to 150. Total range is
Okay.
120 degree.
Is there a way to do that digitally in the uh, with the optics instead of having to rotate an entire mechanical structure?
This is uh well, it's difficult in the case of AfPS. There is a we can just bend the direction of the path, or there's the electron using this electric field, but for the photon is the it's no way to bend. So
No.
there's a we need to rotate the whole spectrometer.
Hmm. Hmm. I was thinking like in a way that like there's these phased array radar systems. They use beamforming to but I think they don't need the high quality of the beam that you need. Um,
Deforming the what?
Say again, I didn't miss the last part.
So you mentioned the deforming some optics or what?
Yes, yeah, using beamforming optics.
Okay, then the beamlines. Sorry, this is maybe this. I'm not getting the question. This is so. Looking at the
So you have the photons coming in, they impinge upon the sample, and then you're rotating this whole mechanical structure so that you can
yes,
integrate over all angles, right?
mm,
And
yes.
I was wondering, is there a way to um, do that with a some kind of mirror system in the beam, or yeah, to intercept the beam with some kind of mirror system so that you don't have to rotate this entire mechanical system?
Uh,
Probably
yeah.
not, huh?
So yeah. So if we can prepare that a lot of mirrors, a lot of detectors, so maybe we don't need to rotate. So that in one shot we can measure the different angles,
Yeah.
but it costs too much.
It probably costs too much. This is easier to rotate it, to rotate this mechanical system.
Yeah.
Uh, that's interesting. Are there any questions for the speaker? What is your beam?
Hi,
Oh,
Jun. Hi,
hi
Jun.
Toshi,
This
go
is
ahead,
Toshi.
please.
Yeah. Thank you for joining us and thank you for your excellent talk. And my question is,
Yeah.
what is the most important factor to achieve your designed resolution?
Okay. This is I cannot say that only one factor. This is all the factors must be the best. But now that's the biggest factor limiting the resolution is the quality of gradient. So uh, of course we need the good light source, ring, and the beamline, optics, also the mechanics, and also the control system. Everything must be the best one. But yeah, here you can see that in the for the high resolution one, we achieved the design ones. So all the optics, all the mechanics is okay. But for ultra high one, it's the present one is not reaching the design one, and this is mainly due to the quality of the graded. But this is not the problem in the companies, but I think that this is the current limit of the technology or economics also includes. If you can invest this huge budget, maybe we can reach this one. It costs too much, so we cannot ask the company to develop this high quality one.
Okay, thank you.
Yeah.
What what is your schedule for proposal cycles? Like when is the next closing?
This is every half year. Actually, the next one it was just closed. The proposal call was closed.
Okay.
Maybe two days ago. So next one is yeah, half years later.
I guess it'd be like in May or something like that.
Yes, yes.
Yeah. And when is your next users meeting? So or workshop or tutorial for using the beamline?
Actually, this is yeah, for this domestic purpose, we are planning to have that tutorial session next year. But that is not international one. It's totally only for Japanese.
Mm-hmm.
But actually, we're too busy to just commission it. There's a probably there's a international user meeting will be. Yeah, we need to think about that. Yeah, no,
Okay.
nothing. There, not
Right, nothing's on the
planned.
radar. Okay.
Yeah.
There any other questions for the speaker?
Yeah, I've raised my hand since.
Yeah. Okay, go ahead. I didn't see you.
John, thank you for very a nice talk on this very interesting technique, Riggs. So I'm wondering, I have a couple of questions. One is, why is it very challenging to have very good signals on powdered materials? So you often need this single crystal to be able to have high resolution. I don't understand why it is that way. Because my interest is to look at battery materials and catalysis. And then you're challenged by the fact that, okay, yeah, if you have, if you want to do something like XSMD, then it's not, you don't get very good signal if you use powdered sample. So is there a way to overcome this?
This in principle, it is there. If you use a single crystal, by changing the detection angle, we can measure the dispersion. But if you use the powder sample, not single crystal one, so we cannot measure the dispersion. But we can measure the some average one. So that information is okay to discuss some your sample. Yeah, you can use the powder sample. But the specific problem is in this spectrometer is this one it is there. If the sample surface is rough, it is the analysis becomes a bit complex. This is only happens to our spectrometers. The conventional ones, it's gives us just one spot. So that even if the sample surface is rough, we don't care. It's okay. So this problem it is only 4 hours, but yeah.
And do you accept a proposal from outside Japan? Is it open to the public?
Yeah. It's open to this there.
Okay.
All countries. Actually, roughly half from the proposal is half from the abroad. It's not half from the domestic, half from the Europe and the United States. Yeah.
Okay, I do know that RICS is a very a bit difficult, very competitive right now. So what is the success rate for this? I would like to apply at least that. So we do a diamond, but I would like to also expand my use of this to also Japan. So what is the success rate for the application?
Roughly this is a 2.5 to nearly 3. Sorry.
3%. Oh, 3 thought. Okay, yeah, okay. Yeah.
So roughly the accepted one is the 10 proposal, but the application was nearly 30, 27 or 8.
Okay, yeah, okay, so that's quite low as okay, yeah. Okay, yeah, I will be exploring that. And also maybe final question is that do you have, because the data interpretation is still a bit, not many people can do that. I do collaborate with Frank De Groot, who is also one of the experts there, but is it also, do you help with the data analysis and interpretation sometimes?
It is optional. It is the facility doesn't offer any it is optional. It is data analysis group or something. That is so we need to user has to find this collaboration with any calculation theoretician.
Okay, specific calculations. Okay. Thank you very much. I'll be getting back to you on this because I try to use Grix these days for battery to look at my battery materials, also catalysis. Okay. Okay. Thanks.
Thanks.
Any other questions for the speaker? Can I ask one last question then? You briefly showed a biological example where you were looking at myoglobin and you were determining the charge state. Can you do that as a function of temperature and as a function of oxygen binding? Does the sample have the sample chambers have some kind of way to like introduce a substrate or gas? So I'm thinking I know for myoglobin, the charge state or the spin state might change upon binding of the O2.
But unfortunately, it is that our sample chamber doesn't allow there to apply the insulating gas. So now we can only accommodate just a solid sample.
Yeah. Okay. Well, thank you again, and we hope to hear more from you in the future of a school that we could attend or a school that we could actually even organize by Zoom at first, and then maybe in-person workshop in some subsequent year.
Thank you.
Okay, if there's no other questions for the speaker, then we'll close this session and go on a break for about 25 minutes. Thank you very much.
Thank you.
Thank you. So our next speaker will be Dr. Kun Shin from NSLS2, and he will be speaking about how AI is changing the way experiments are done at synchrotron light source facilities. That talk will start in 20 minutes. Hi, Kun. This is Lawrence. You can test your slides if you want. And you can test your audio as well.
Okay, so let me try to share.
Mhm.
So do you see my slide?
I do, yes.
Okay, that's good. And it's advancing.
Yes.
All right. Looks good.
So how are you doing? Were you guys you worked through the shutdown, right?
Yeah, yes, that's true. Yeah. So we're a contractor. So we're not like the Commerce Department NIST, for example, National Institute of Science and Technology. So they are federal employees, but we are not. We are contractors.
Yeah.
So so they actually really shut down. So as you know, NIST operates 3 beamlines on our facility.
Oh my
So
goodness.
during the past couple of months, essentially those beamlines were shut down. And
And
it actually
did they
takes,
require daily maintenance? Like somebody has to keep the pipe
yeah,
sets and all
no,
that?
they couldn't be here. So that's why they really put it in a safe mode.
Okay.
So when they are back in the past few days, they are spending a lot of time trying to get the beamline to an operating condition. So
Mm,
they are not taking users as yet.
I see.
So it's like yeah, you mothball it in a sense during a shutdown. So yeah, but we're okay. So we usually have some leftover funds that can allow us to bridge some of these type of situations. Um, but yeah, we were definitely concerned in terms of and we whether we need to furlough people and so on. In fact, the whole laboratory is also um, was also preparing for
Mm,
something like that. Um, but fortunately, we didn't have to practice uh, in the end.
wow.
Yeah, lots of uncertainties and all these things. Things happen. Yeah.
Is Noel still on the staff?
Yes, yes, he's still there. He's now broadened his scope to do workforce development and so on.
Hmm.
So he organized a couple of meetings in terms of outreach to nearby universities and so on. So we were participating in those. Yeah, he's doing reasonably well. So yeah, it's um it's it's been good. I guess it could be worse, but in the
Yeah.
end, it seemed to work out. Yeah.
So do you have a long range plan for upgrade? What's your next sort of
Yes,
dark period?
yes, we are planning to have an upgrade. We put in a proposal. I think I may have mentioned it in the past. We put in an upgrade proposal 2 years ago, maybe even 3 years ago now. So that received what's called the CD0, which means mission needs. So that's
Hmm.
already on the radar in a sense at DOE. Um, but recently there has been no progress along progressing that project as yet. So with the government shutdown and budget situations and so on, we don't know when the project may be moving forward. But
Yeah.
we hope that's still on the agenda. So our original plan or in the proposal was that we could start doing something like R&D towards that upgrade plan in maybe before 2030, and then get the actual project completed maybe in the mid 2030s.
Hmm.
So that's still something we would like to see. But right now, there's no feedback on that part as yet. As you know, we have a project to develop new beamlines, to
Hmm.
add new beamlines. That's called Next 3 project. So that one is ongoing. It also faces a bit of uncertainties due to the shutdown. But we believe this is going to be continuing and will receive reasonable funding in the coming year also. So that's the main construction project that we're pursuing. And we view the the whole facility upgrade will be a longer term.
Yeah.
So that's okay. Yeah.
Who did they make as SC1? Was it like a reasonable person? Or I guess you can't say, but did you hear what happened at O&R? Where they
Oh, no, actually, I,
so they removed the admiral that was in charge of O&R.
oh, no, I have not heard about that.
They
Yeah.
put in a someone, I guess not an admiral.
Mm,
And yeah, I don't know.
interesting.
I mean,
Yeah, we are not seeing that on the DOE side, on the Office of Science side. I think, especially on the facilities, the same program manager are there, even though they did lose a few people as the division directors and so on. But on the ground level, people are still there and they're familiar with the situation and all these things. So
mhm.
we're reasonably okay. No big changes. So okay, so that's news on the on that area. So
Yeah, okay.
yeah,
All right, I guess we're actually at 2 o'clock,
okay.
GMT plus 2. So why don't we go ahead and get started?
Yes.
Um, our next speaker is Dr. Kun Shin, who's the Deputy Director for Science at the National Synchrotron Light Source, NSLS2, which is located at Brookhaven National Lab in Upton, New York, in the United States. And we thank you for being here, a longtime friend of the African Light Source Project. And you got a very interesting title, so I'm all ears. I'm sure we all are.
Okay.
Go ahead. Thanks.
Thank you very much, Mr. Chairman. So I really appreciate the invitation to speak here again. I always enjoyed these meetings, and I was fortunate to be able to attend in person. last year I met many many researchers in the continent. So I really feel this is an excellent conference series which started back in 2015, which I also attended. That was held in Grenoble, if I recall. So when I was invited to give this talk, I thought I would do things a bit differently compared to what I did before. So in the past, I think I always try to show highlights from our researchers and to illustrate the type of science that are going on at our facility. But these days, I'm sure you all have heard, there's a lot of talk in artificial intelligence and machine learning and all these things. So I thought I would change my talk title a little bit. So I will talk about how AI is really changing the ways experiments are done. I think in lots of areas, but certainly at the light sources. So that's what I want to do. Although I will still give an introduction about our light source, and I'll show the science programs and highlights. I'll illustrate some of the industry programs, which I perhaps didn't mention in the past. And during the in-person meeting last year, there seemed to be interest in that, so I will mention that. I will have one slide on strategic planning that we did in the past year for future development. And then so that'll be maybe half of my talk, and the other half will cover this question. Can AI bridge the knowledge gap and help users and light sources? We believe that's going to be the case. I'll show an example that I borrowed the slides from Dan Oates, some of you may know, who's leading a new beamline development project on high resolution diffraction. So essentially, I feel that AI could be a bridge connecting and engaging the different communities. This will help develop local workforce and also consistent with the Sustainable Development Goals from the United Nations, particularly in these other areas that we usually don't necessarily connect directly. So this may enable quality education, reduce the gender gap for researchers, as well as other areas. So I will try to do that. That's a few new slides that I borrowed from Dan Oates, and I hope that will generate some interest here at this conference. So, and then I'll summarize. Okay. So I will still start with what NSI's tool or National Synchrotron Light Source Tool really is. So this is the area view of our facility. If you imagine you're going in from the entrance at the in here, I guess I should do pointers. So here's our main entrance. If you're going into the main entrance, then you go through the door, double door there. Then you would see our facility. Basically, this consists of beam lines, which are these tangential lines from this circle. The circle represents the actual accelerator or storage ring. So the storage ring itself is about half a mile in circumference. And then as we inject electrons at very high speed, very close to speed of light, and then we use magnets to guide the electron bunches along the circle. So as the electrons are passing through in this orbit, it'll emit what we call synchrotron radiation, and that's along the tangential directions. So when we want to use these synchrotron radiation, we open up a hole in the vacuum chamber that for the electrons. We build beamlines along the tangential direction, and we can have different type of beamlines. It can be doing diffraction scattering or spectroscopy or imaging and so on. So that's how a synchrotron light source looks like. And the reason the synchrotron light source is very useful is because that the synchrotron light can really extend our vision and see things that we could not see. So the synchrotron radiation wavelengths usually covers from infrared through visible to ultraviolet and to very hard X-rays. And this is the area, this is the type of electromagnetic spectrum that actually allow us to see these things from atomic level to molecules to maybe some viruses and also other type of small things that's hard to see. So essentially, the synchrotron radiation would cover the broad energy range from infrared all the way to very hard X-rays. And we have different techniques that can allow visiting researchers to do all kinds of science, from studying superconductivity to electron transport and molecular vibrations in the infrared, and all the way to magnetism, to study environmental samples, and also batteries. And there's a huge part of synchrotron application is for drug discovery, as many of you know. We also have possibilities to look at real large things, for example, on the additive manufacturing side. In fact, we're starting a new project to develop a dedicated advanced manufacturing beamline to allow in situ studies to be done to see how microstructures are affected by new types of manufacturing processes and so on. So this is basically an overview of what the light source can be useful for. I think you have seen this perhaps in various presentations, but I also want to just let everyone know. Now, back to AfLS 2. So we have been, oh, I see a hand raised. Is there a question there?
I think that's left over from the last session.
Oh, okay. So that's all right. Yeah. So
Yeah.
I'll continue. So we started our the AfLS 2 construction project back in 2008. So it took us 7 years to complete the construction project, and we transitioned a number of beamlines, new beamlines into operations in 2015. And since then, we have been aggressively developing new beamlines. And right now, and this chart simply shows that during the first 4 years of our operations, we bring on average one new beamline into operations every 2 months. So that's a very steep slope. And then after 2020 or so, we focus more on operations. So that has slowed. But now with the new next 3 project, we are ramping up the pace again. But I don't think we'll ever do this anymore because we also need to operate. We need to also operate a storage ring to allow to support users. So our goal is to have 45 beamlines in operations by 2035. So that's our beamline development. And our users, I think I always show this. We have an excellent user program. And on the left side, it shows the word clouds based on user proposals in terms of what they study. As you can see, one can study catalysis, one can study structures, batteries. Many of these experiments are done in situ, which means under real operating conditions, and so on. There's also dynamics and studying phases and all kinds of things. So since the start of the operations in 2015, we ramp up the number of users in the first 4 years very quickly, and then the pandemic hit. So we were affected by that, and now we're back to. Actually, let me minimize that. And we're back to ramping up the user numbers. In the past couple of years, we saw a greater jump in terms of number of users coming to use our facility, and that was mostly due to the AfPS shutdown. As you know, the other light source in Argonne National Laboratory, advanced photon source, went through an upgrade in the past couple of years. So that shifted the users, some of their users, to our facility. And now we're sort of seeing it's leveling off to around 2,300 users, unique users at our facility. Now there's all kinds of science done at the light sources. In fact, all over the world. I think at this conference you probably hear a lot of different examples. So I'm not planning to show these examples again to save time. So this ranges from batteries to molecular structures for structural biology, to look at the virus structures and so on. A lot of materials development, and as I mentioned, advanced manufacturing. And here in the US, there's a huge interest in microelectronics to develop how the synchrotron light sources can help advance the microelectronics technology in terms of chip making and so on, and environmental and all kinds of things. I also have two pictures here showing we're also pursuing cutting edge X-ray technology. This is to the bottom right is you developing focusing optics for X-rays to focus hard X-rays down to nanometer scales in terms of focus size. And on this one is we're developing a new methodology to do quantum imaging. This and so-called maybe ghost imaging. So there's a lot of interesting development in those areas as well. Now, there's a lot of highlights. Again, I don't want to go through the details, and these are just some of the journal covers we had in the past year, in the past fiscal year, I should say, which ends September 30th here in the US. Again, I don't want to dwell here, so that's that. And I think last time when I was visiting this conference in person, there seemed to be interest in industry research. And I actually thought I should show this. We have a pretty strong industry research program that's actually led by Dr. June Wang, who happens to be my wife, I should say. Since in the past 4 years, we have seen increase in terms of number of companies using AnalSat 2, and that's the chart on the left. And if you look at the usage per beamline, oh, I should say there are two ways to do industry research here at the light sources. One is you can come here as a general user, just like everyone else. So that's free. You don't have to pay for the beam time. However, you can also do proprietary research, which means that you don't intend to publish. So we allow that to happen as well. So the chart on the right shows the proprietary shifts used in the past 4 years. As you can see, the vast majority of these are structural biology. Those are the green bars. So that's because there's a lot of drug company and to develop new drugs and so on. So that's a snapshot in terms of usage here. So on average, we see maybe a few % of the total beam time at AfLS goes to proprietary research. And that's largely focused on structural biology beamlines. So if you just look at the structural biology beamlines, that's about 10% of the beam time going to proprietary research. So that's that. We also do a lot of strategic planning. I think I probably mentioned this before, but this last year we conducted a number of science driver workshops, or we call it the brainstorming workshops. That's shown on the bottom. This includes microelectronics, quantum information science, energy and catalysis, synthesis and manufacturing, human health, earth and environment. And we also have 2 support areas, that's data science and infrastructure. In fact, I'm going to talk next about the data science. And obviously, accelerator is a main component of our facility. So we have R&D in that area as well. Now, the process we did this last year was we conducted these brainstorming sessions, and then we tried to connect to the basic research science focus areas. So essentially, we identify the basic science questions and how synchrotron capabilities may help to address those questions, and what are the opportunities at our facility. So that's the process we have been using. And so the final product is a strategic plan for the next 5 years, including last year, 2025. So that's posted online, and you're welcome to look at, to read it if you like to see our new strategic plan. Okay, so that's okay. So there's a lot of evolving science emphasis and these days, and one particular one we're paying close attention to is critical minerals. I'm not expert in here, but I read this article that's posted there. There's a lot of discussions in terms of the how to mine these critical minerals and how to purify them and develop them into something that's useful and so on. So there's a map based on geological survey in the US showing where potential these different critical materials critical minerals can be found or have been found. So I just want to show this there, and this may be related to the initiatives here at African Light Source, because I think there's a lot of possibilities there in terms of developing research and R&D and development areas in the critical mineral area. I'm sure the whole continent has a lot of opportunities there. So I just want to bring this up here in my talk. Okay, so I see that's already 20 minutes. So let me just go to the second part of my talk. That is, can AI bridge knowledge gap and help our users at light sources? So let me go through this. The following slides are mostly those are addressing the UN sustainable goals. So I borrowed several slides from Dan Oates. Some of you may know him. He's the beamline scientist at the pair distribution function beamline. That's circled there. That's him. And he is also leading the development of our brand new beamline that's part of the Next 3 project that's called high resolution diffraction beamline. So he has done a lot of work in in connecting with AI and employing AI in high throughput research. So I thought it may be of interest to this audience. So for the Next 3 beamline project, we are calling it. We want to develop beamline 2.0. Essentially, when we design and construct new beamlines, we want to really think how our future users may interact with beamlines and obtain data. So the goal here is really to create the next generation of beamlines that focus on the full end-to-end experience for our users. So this will definitely have the potential for rapid discovery, improving productivity, and certainly maximize the scientific output. So that's sort of what we're thinking. So incorporating digital aspects of things, AI, into our operations. So the following slides are, again, from Dan Oates. He has several areas, but I don't have time to do that. So I picked one of them, that is AI tools for automation. So here's an example Dan provided. Essentially doing combinatorial sample research that's from multiple target enabled sputtering deposition. So I think some of you may know, so you can have deposition from different sources, these 4 sources, for example. And then when you do sputtering deposition, you simply spray different atoms onto let's say a substrate wafer, and then in the end, as you can see, because of the locations of these targets, so in the end you have a mixture of the atom sources on your wafer. So the question is how we are going to map the structural phases on this wafer. Now we do X-ray diffraction. That's exactly what Dan did on the PDF beamline, pair distribution function beamline. So he did estimates in terms of if we want to do very careful measurements, and the total possible number of measurements on these wafers will be something like 18,000 measurements. So the typical measurement time at this beamline is about 10 seconds. That's already pretty fast. However, if you want to sample all 18,000 points, this may take 2 days. So the question is that maybe to do all these measurements at every point is not necessary. So what measurements that we can do to speed up this measurement process, at the same time obtain the information that we need. So the group considered maybe 3 approaches. The very first one is just grid scan, as many of us did during our careers. You set up a scan and you walk away and come back and check to see how scans are going, and eventually you get the complete scan. So that's the old approach. One can also develop certain AI-generated algorithms to allow automated analysis. And that way, this can help users to conduct experiments in a more effective way. Now, the third one is really to rely on AI to actually design and drive the analysis based on its own analytical thinking. So that's what Dan did in this example. So AI-driven measurements. So I want to show this because I thought it was very interesting when I first saw this. So this is a sort of like the data that's already having maybe 49 points, 41 measurements done, and it gave you this map already. And then you can go on to collect more data. So as you can see, as the AI-driven data collection progresses, it refines the map of the structures. And that's based on whatever the points they want to, the AI would like to measure. So that's the red crosses that you can see. So this is not driven by our beamline scientists, but by an AI machine. So, and as you can see, maybe after 500 points or so, or 500 measurements or so, you see more or less this type of structure stays. So there's not too much progression. So essentially, we're seeing the mapping converges into something that should be very much representative of the actual reality. So this shows that instead of doing all 16,000 points, only, as you can see here on the top, only with 800 measurements, you essentially get 99% of accuracy in terms of what the actual distribution of the structural phases are on this wafer. To me, it's really amazing how he did this. And he also showed, this is all from Dan, so I gave him full credit on this. So this also shows that you can do random sampling, you can do geometric series and all these traditional ways. But AI-driven is really allowing you to converge onto a real model very quickly. So that is something that I feel is going to be further advanced and perhaps to other techniques. And this will really help our users and staff to conduct experiments more effectively. And with AI, our users may be able to really conduct very smart experiments rather than wasting beam time doing something else. Okay, so I think I'm almost done. So essentially, you have seen this from my previous discussions and presentations, and now I want to add, we all realize that the beam time is very hard to get. It's very precious, and our goal is to get more people, more users, more access, and better data. So that's our goal. However, doing all these are hard. So AI, science is, as we know, is very challenging to really think it through. This is perhaps where AI can really help, and this will allow perhaps all users to be able to conduct intelligent experiments and not wasting too much beam time while exploring on their own. So that's I think that's all I have. So this is a quick summary that we are a hub for a network of capabilities, users, and partners, and tackling our challenging problems. We have seen tremendous growth in the past 10 years, and science output is increasing. And the second part is AI-driven experiments we feel are going to be very important at NSS2. And this would help to remove the barriers for non-expert communities to use cutting-edge tools for their research in a very effective way. So I think there's a lot of exciting future in this area. So I want to share with you. That's all. Thank you. And here's a photo with Dan and his colleagues at PDF Beamline. Thank you very much.
Okay.
Yeah.
Well, thank you. Thank you. I think we have time for a few questions for the speaker.
Okay.
I don't know if there's anyone in the chat. Anyone wants to raise their hand? You could just unmute yourself. I sort of have two questions.
Sorry.
I have a question about your future plans for beamline. So we the African Light Source talk a lot about the quote unquote African beamline. I imagine the NSLS2 might be available and have space for African investment in a NSLS beamline, like any
Yes.
facility. Yeah.
Yes, though I think that's a possibility. Oh, I forgot to show a slide with a number of beamlines. But as you know, we have our full capacity is something like 58 or 60 beamlines, and right now we have 29 beamlines in operation. And the new next three project will bring additional up to 12 beamlines into our facility. And we have we have another couple of beamlines in operations. So in the end, actually, let me go back. We
It's
have
probably the case
45.
that
Yeah, we have 45 beamlines under develop. No, we will have 45 beamlines by 2035. So that's our current. Yeah, that's this one. And as you know, we still have room to develop maybe additional 10 beamlines beyond that.
Yeah.
Beyond the 45 beamlines that's already in our plan.
It's
So
probably
I think
also the case that by
Yeah.
the time you get to 45, it'll be time to redo the early beamlines again.
Well, that's true. We need to keep them up to date. But that's different. We have certain operating funds to allow us to maybe replace detectors, for example, to do minor upgrades and maintenance. So we hope at the DOE there's separation between construction funding versus operating funds.
Right.
So construction funding is hard to come by, so we would like to reserve those to construct new beamlines. So the next maybe 10 beamlines beyond the 45 that's already in our plan could involve maybe a beamline for the African light source. We would love to discuss that somehow.
Sure. Okay.
So there's room there, basically.
Right.
Yeah.
Are there any other questions for the speaker? Then with that, we'll thank him again. Oh, go ahead.
Yeah, Lawrence.
Yeah.
Yeah,
Phil.
yeah, yeah. Okay, nice presentation, Queen. My question is: I know in the past, NSLS to organize a like a synchrotron seminar for across the continent, especially for the African continent. But what are any opportunity or anything that you have for the Africa which we can make use of? For the African researchers. Is there anything that you want to pass across?
Yes, so we're certainly still interested in doing that. So in the past year, we sort of we have been slow in terms of coming up with a real plan, but right now we're planning to do something along those lines. It'll be a remote lecture series, just like what we did before. Perhaps in the new fiscal year. So which means maybe in the summer or in the fall of 2026. So that's what we're planning to do.
Okay.
Okay.
So in terms of the if we are planning to use your facility, is there any little mobility funding for the researchers from that side?
Yes, so we can do something along those lines. I think we are also supporting the FAST, I guess faculty student groups from IU supported by IUCR. So that's another avenue that one can use to come to our facility and to other facilities in the US to conduct research during the summer next year, right? So that's, I think it's usually in the summer. So that's definitely an option. I would encourage people to go through the process and submit their proposals and so on. And I think that's managed by IUCR, if I recall. So that's a good avenue. We support that we supported this in the past and will continue to support the groups.
All right. Thank you.
Sure. Yeah. Thank you.
Okay. Okay, so now I'll just turn the session chair over to Dr. Jakarta Kudawashi from the Diamond Light Source. And so the next several speakers will talk to us about the X-ray imaging platforms at Diamond. So Kuda.
Yeah, good afternoon, everyone, and thank you for joining. I think because we're out of time, I'll just hand over directly to our first speaker from the Diamond Light Source, Julia Parker, who is the head of the Imaging and Microscopy Group at Diamond.
Thanks, Kuda. I'm unable to share my screen at the moment, and I think you have to allow me to.
Yeah, Lawrence, can you help us with that?
Yep, got it. Sorry. Behind there.
Yeah. Okay. Just put it in presenter mode. Can you see that in full screen?
Yes.
Okay, brilliant. Okay, so yeah, thank you very much, Kuda, for organising the session and inviting us all to talk. So my name's Julia. I'm the Science Group Leader for Imaging and Microscopy at Diamond Light Source, which is the UK's synchrotron facility. So I'm just going to give you a very brief overview of the facilities we have within the group. There's some follow-up presentations from lots of the beamlines, so really I'm going to focus on how we can look at the group as a whole and how you might want to make use of the different modalities, the different length scales and time scales within the group, going from kind of large volume, micron resolution, all the way down to kind of atomic scale imaging with the electron microscope, and some idea of some of the science that we do, focusing kind of on some in situ applications. So as I said, Diamond is the UK's synchrotron facility. We've been operational since 2007, and we're just kind of going through the planning and the preparation and the design for our upgrade project. So we will be shut down for 18 months from December 2027 to put Diamond 2 in place. So obviously it's an upgrade to the machine itself to a fourth generation source, some new flagship beamlines, but also some upgrades to our existing beamlines to make them able to kind of exploit the new source. So as well as the beamlines, we also have some electron microscopy facilities for biology and physical sciences. So that's EBIC and EPSIC. EPSIC sits within the imaging and microscopy group. And the idea here is to really exploit the complementarity between those two techniques and kind of how can we drive experiments that kind of need both of these modalities and gain from the expertise of having them here on site rather than them being distributed at other places around the country. So Diamond itself, we always say we're in Oxford, which is kind of west-ish of London, but we're not quite in Oxford, so it's not very Harry Potter-ish as you look around us here. We're on an old airfield site. Previously, so in 2007, there was lots of green fields, but that's kind of built up into more of a science campus around us, and we're actually sharing the site with ICIS, which is the UK's neutron source, and their central laser facility as well. There's other kind of institutes growing up on sites such as the Ada Lovelace Centre, which is really kind of a hub for scientific computing for large-scale facilities. So we have lots of collaborations with them, looking at how we're using AI for data analysis, how we're building faster algorithms, and how we're using kind of data analysis services as well. As we go towards our upgrade, we're going to have faster, a lot more higher volume of data. So having those on site is really helpful to look at how we have that infrastructure in place for our users. So Diamond itself, we have, I think, I always lose count, but I think it's 33 different beamlines, and they're divided across 8 different science groups. So we kind of have the macromolecular crystallography beamlines around one side of the ring. We have surface science. We have crystallography, which kind of covers powder diffraction, single crystal diffraction, and pair distribution function. And then there's spectroscopy and bioimaging. There's a lot of overlap with what we do with the bio-cryoimaging as well. So B24, around the other side of the ring to us, is actually our soft X-ray tomography beamline, where they're imaging cells in kind of a frozen, hydrated environment. And there's lots of work going on in how can we then translate that to bring the samples across to maybe correlate that with some chemical imaging that we might be able to do maybe at the X-ray nanoprobe. So in imaging itself, we have IO8, which is our soft X-ray scanning microscope beamline, and that has now 2 end stations. So we have the STIXM for kind of chemical mapping and analysis, and then we have a soft X-ray tychography branch line there as well. DIAD is our dual imaging and diffraction beamline, so you'll hear about that from Sharif later, but it's essentially we have two beams hitting the sample. We have a large beam for imaging, and then a focus beam which we can raster across the sample for diffraction mapping. So you can combine the two. You can do your tomography, you see an interesting feature, you can use the diffraction to map across that feature and see what the composition or the structure is. I12, Genevieve will tell you more about later, but this is our high energy beamline, so joint engineering, environmental and processing. And the idea here is, again, it's a large beam, it's very high energy, so we get that penetration into large samples. We can do things like look at the structure through imaging and diffraction, again, of large scale materials. So something like a turbine blade was one of the first samples that they looked at on Jeep to look at the stresses and the strains in the component as a whole. I13 is actually 2 beamlines, so we have I13-1, which is our coherence beamline, and I13-2, which is our imaging beamline, and those are situated in a satellite building outside of the ring. And then in another building next to that, we have our hard X-ray nanoprobe, and that's nicely located with the 2 Joule arm microscopes that make up EPSIC. Okay. So, as I said, the kind of beamlines in the group, we use different techniques. So we'll have imaging, tomography, in full field techniques, absorption contrast, phase contrast, combined with maybe diffraction mapping. And then we have kind of scanning probe techniques where we're using maybe fluorescence or spectroscopy mapping or tychography to give different length scale information about your sample. And essentially that means you can start up at this kind of micron length scale, looking at a large field of view on a whole component level. And as you go down in field of view but up in resolution, you're then looking at kind of nanoscale information all the way down to atomic scale information at EPSIC. And not all of these beamlines are within the imaging group, but it's really important to think about how we work with beamlines from different groups. So there's overlap in terms of our resolutions of fields of view, but not so much the techniques with maybe our microfocus spectroscopy beamline and an IR beamline. And these can really complement what we're learning from the imaging and the diffraction, carrying that over to spectroscopy and infrared. Okay. So in terms of imaging and microscopy, really you can use these different techniques in different ways to build up a picture of your sample. So if we think of traditional full field imaging, you might be looking at differences in material density to look at the pore structure or crack growth within a component or a sample. But if you combine that with the scattering or the diffraction information, you can then add in things like the crystallography. You could begin to look at the composition of your sample, how the strains and stresses are distributed within that volume, the orientation of the crystallites, which is really important when you're thinking about something like bone and teeth and how those crystals are orientated to really give the strength to the material. Or you can start to look at dislocation growth throughout the sample. And then you add in another component, so you have your imaging, you have your diffraction, your scattering. If you add in your spectroscopy, this is then going to give you information about the elemental composition within your sample. So you can use fluorescence mapping to look at how the elements are distributed. You can combine that with some spectroscopy to say actually what the chemical state of those elements. So you might know that you have different concentrations, for example, of iron within your sample, but you want to know what are they iron 2+, iron 3+. You can get that from the spectroscopy. You can go back to your crystallography and look at maybe the different ion phases. So if you're looking at corrosion, you could then see what iron oxide phases you have coming in at different points and whether this is correlated to maybe cracks or voids within your sample, for example. So putting that picture together to give you the whole view. So as I said, within the imaging group, we have kind of this wheel of different beamlines and different techniques. I just need to hide the view there, sorry. So in terms of I13-2, which is the I13 imaging beamline, I12 and dyad, we're really kind of this full field imaging type approach. This can be used to look at kind of the whole scale kind of biominerals, or if we're looking at a battery, you might be looking at the whole battery as a whole, or an in situ component of that. So it makes like a pouch cell or a coin cell makeup within the beam. You can look at kind of large-scale geosciences, look at how things are distributed within soil, how things behave when they're crushed, or nuclear waste remediation and stress strain imaging. And if we look at the other side of the wheel here, we kind of have more of our scanning probe techniques where we're looking more on the nanoscale composition and we're combining these with spectral imaging. So if, for example, you're imaging your battery as a whole on one side, you might be then looking at maybe dendrite growth within that battery on the other side of the techniques that we have available. And this kind of difference between the full field imaging and the scanning probe techniques gives us differences in, as I said, the field of view and the resolution, but also really in the time scale that it takes to measure. And this really impacts on what we can do in situ. So these full field imaging techniques can be really fast, but we're limited to kind of micronish scale resolution, but we're seeing a large field of view. So you could be cycling and decycling a battery and getting kind of millisecond resolution on your time scales as you change something in situ. With the scanning probe, it's a much slower technique. We're having to raster our sample through the beam. And really to do something in situ is taking on the order of minutes or even hours for some of these techniques. So then you really have to think about, well, if you're looking at an in situ process, really you want to be looking at something where you can make a change and then it's stable and static while you take the measurement. So for example, on the nanoprobe, I'll talk a bit later about the cells we have available there. We've done a lot of work on catalysis where you can change your gas flow and your temperature. You oxidize, for example, your material and you look at how that oxide phase is distributed throughout the catalyst active material, and then you can reduce, and these things are stable in between. It's very hard with the scanning probe to get those intermediate timescales, as it's changing. But as we go towards Diamond 2 and kind of faster techniques, this kind of really starts to open up the speed with which we can do in situ and kind of then makes it more comparative with the large field imaging as well. Okay, so one area where this kind of ability to look at large scale micronish resolution all the way down to kind of nanoscale resolution really has an impact in is bioimaging. And I think you're going to get a lot more examples of the different science from the beamline talks that follow, so I just kind of wanted to give a flavour or an overview. And really, if you think of using these different capabilities within the group, you can look on the length scale of kind of bones and joints. This is actually not a living creature, this is a fossil, and this was imaged on I12. And they were able to see the structure inside the fossil and look at how the scales in this kind of, I think it's a wing of a petasaur. Genevieve will probably correct me. But you're looking at that kind of length scale. Dyad, we can, on a similar vein, look at things like bone material, but you can combine your imaging with some diffraction mapping. So you can kind of focus in and look at how the changes in the crystallites, in how they're orientated or in their crystallographic parameters as your joint is strained. So you can look at the impact of that external strain on the bone, the hydroxyapatite crystallites themselves. Or if we go to the I13 imaging beamline, we can look in detail at the structure inside a joint. I think this was a knee joint as it was flexing. Or we can look at the structure, for example, inside a bumblebee eye. And then we can kind of go down to the next length scale, and this is looking at the wing of a moth. So here you can see the structures that make up the wing of the moth, and if you combine that then with some tychography, you can look actually what does the structure of these individual scales look like. So you're kind of piecing together the picture at different length scales as we go down. And I14, so the hard X-ray nanoprobe, here we're combining the chemical information. So this is looking at this kind of cellular level. These coccolithophores are single-celled organisms that live within the ocean, and they create these calcium carbonate kind of formations around them. And here we're looking at the distribution of calcium and strontium within those, and we can do this using XRF tomography. And here we can see it's not an even distribution. There's kind of this stripy distribution to the coccoliths. So again, you can kind of think about how you can combine that with, you can look at an assembly of those, and then you can really hone in and look at what's happening in an individual coccolith. An example of users using these techniques in different ways and combining them with kind of lab techniques to get a kind of correlative picture is an example of the structure of enamel, so tooth enamel. And here they've created their sample using the fib milling, and they have this tiny little piece of tooth enamel where they've slightly demineralized it to look at how kind of tooth caries grows. And they can do some lab analysis using SEM, where here we're getting a picture of the surface of that fib section. But if they bring that to I14, they can add in the chemical map. So we can look at the distribution of calcium within that structure of tooth. And here we see kind of these rod and interrod regions that make up the structure of your tooth enamel. And here, because we've had some demineralization happening, you can actually see the intensity of the calcium in these rod regions is much lower than the interrod. So these are kind of being dissolved away faster than the interrod as we start to form the tooth demineralization, which eventually would lead to caries. And we can see that again in the differential phase contrast imaging, where you have kind of this higher phase density or higher mineral density in the interrod regions. But what's actually happening within those rod and those interrod regions? What's making one of them more or less resistant to this erosion? And here they've combined this with soft X-ray tychography at our I08 beamline, where you can really start to see kind of the alignment of the individual crystallites within the rods and the interrods. And actually it seems that the rod regions are really highly orientated and the interrod regions are not so much. So again, they're trying to answer the question, what is it about the structure of these regions that's leading to these different demineralizations? Here we're seeing information about the mineral across different length scales. The next step for them is to combine that with what's actually happening to the organic matrix of their teeth to kind of give them the fuller picture. And also there's then the possibility you want to do this in situ. You want to watch what happens as the tooth enamel is dissolved. So we can do that on I14, and I'll talk a little bit about the in situ cells we have there later. So as I said, that was a very brief overview of kind of the capabilities of the different beamlines, and you're going to hear more from the individual beamlines later on in the session. But one beamline I think Majid was not able to make it is I14 beamline. So I thought I'd just give you a little bit more detail, because I think this is a nice example of how it fills between kind of the micro scale of the full field imaging beamlines and the electron microscopy at the atomic scale. So the hard X-ray nanoprobe, beamline I14, is a scanning probe technique. Typically, your resolution will be around that of your beam, which for a nanoprobe is normally around 50 nanometers. And essentially, you're going to focus the X-rays, scan your sample through the beam. You collect the X-rays at each pixel and use something about those collected X-rays to build a map or an image of the sample properties. And you can do this across different modalities. So the most common is using X-ray fluorescence. We can build up a map of the elemental composition. So here we have the calcium and the strontium within a different coccolith. We can add an extra dimension to that if we then scan the energy and repeat these maps at different energies. We can build up a picture of the chemical speciation map within the sample. So here, I'll give more on this one later. We're looking at the corrosion at the edge of an iron sample here, and you can see different phases as it's scanned. We can use the diffraction mapping to look at the crystal structure and strain, but again, we're looking now at the nanoscale rather than the microscale. And if we want higher resolution, we can use tychography here as well. The requirements of this high resolution place a high thermal and vibrational stability on the beamline. It's in an external building here that was purpose-built to house it. And beamlines, nanoprobe beamlines, are often a kind of compromise between the ultimate resolution and usability. You can make something highly stable, but it's normally locked away inside its own room and its own vacuum, and it becomes very difficult if you want to change samples or add in an in-situ environment. So here, this is the picture inside the hutch at I-14. X-rays are coming from this way. Our sample is sat here. We have a fluorescence detector behind the beam, and then we can capture our diffraction or our phase contrast imaging or our tychography using detectors further downstream. And you can see here we are open, we're not in vacuum, we're not cryo-cooled, and this gives us actually a lot more flexibility. So we had a recent project a few years ago to redesign our sample stages. So these are in-house design based on voice coils and flexures that give us really high stability and high precision over quite a large range. So we can scan these over 3 millimeter range without having to switch between kind of a coarse motor and a piezo motor. But essentially we have this large kinematic mount on top where we can fit in different sample environments. And so we really try to optimize how you can get the best sample environment that will give you nanoprobe information, but you could also use that maybe at the electron microscope to be able to correlate information between the two. So we've developed a few different sample environments along these lines using these silicon nitride membranes, these kind of chip designs. So the first one is from a supplier, DENS, and essentially this top part is this whole thing is the electron microscope sample holder that fits into their electron microscope column, but this very top piece is detachable and we can mount that separately on the beamline. So we have the same setup inside the in situ cell, we could have the same sample, and we can easily transfer that, well, I say easily, we can transfer that between the beamline and the electron microscope. And these chips can then be kind of customized or patterned, so we have ones which have a heater patterned on them, so you can flow a gas and heat your kind of 10 micron-ish sample or your powder sample and get your nanoprobe information. Or we can have liquid cells where we flow a liquid through, when we might, for example, have electrodes if we were looking at kind of biasing and how materials were forming to kind of mimic the makeup of a battery. We also have a slightly different makeup cell here, which is slightly easier to integrate for the liquid flow. It's a different manufacturer, but it's the same design. We have these kind of membranes and then the chip setup. And one nice example of using this is doing some spectral microscopy of some battery cathode material under liquid heating conditions. So I said earlier that these scanning probe kind of in situ work is slow. So the time resolution that we're getting here is not great, just kind of looking over several hours, but we are getting chemical information that we can't get any other way. We can't do this experiment with the size of sample that we have here within the electron microscope. So this was work that was developed with Diamond and Johnson Matthey, who operate one of the electron microscopes at EPSIC. And the cell is compatible across the TEM and the beamline. So here we have the sample within the chip. We're heating it and we're flowing the electrolyte to mimic the hot storage essentially of the batteries and how the performance changes. So here we aren't biasing, we're just heating. And what we see is we can use the Zanes maps, the spectroscopy, to tell us about the ratios of the nickel 3 plus and the nickel 2 plus within the material. So nickel 3 plus tells us we have the lithiated nickel oxide phase, and nickel 2 plus means we have nickel oxide. And we see the material to start with had a crack in it, and we're mapping kind of this area of the fib sample. The first thing to do is to flow the electrolyte across the sample, and here we can see that actually we lose a lot of that lithium material as we flow the electrolyte, and then as we store it at elevated temperatures over several hours, we don't see any change in the morphology. So this micro crack doesn't grow. So visually and structurally it looks the same, but actually chemically we're seeing very different things happen. So I think we thought that it would act just like the surface of the material, that we'd have the lithium migrate and we get this interfacial layer form on the material. But actually what we see is that this degraded area of the cathode kind of spreads more from the crack than it does from the edge. So something different is happening within the mechanism. Okay. So that was a very whistle-stop tour of the imaging microscopy beamlines at Diamond. So as I said, we have 7 instruments, and really the idea is how do we integrate these to image across techniques, length scales and time scales to give a fuller picture of what's going on in your material. We have applications across physical and life sciences, from kind of bioimaging to batteries, and there's a real push to how we can exploit these in situ capabilities. So with that, I'd like to thank all of the group staff, and you'll see some of them in the sessions coming up, in particular those that worked on the nanoprobe in situ environment, along with our collaborator from Johnson, for your attention.
Thank you very much, Julia, and especially thank you for including I-14 in the presentation. Yeah. I don't know if anyone has got a question, but I think since we are way behind time, maybe just one quick question for you, Julia, before you go. What do you think would be the main advantages for the beamlines in the imaging group for after the Diamond upgrade, the 4th generation?
So the upgrade will give us much more flux across the imaging beamlines, but also higher coherence. So I think Darren's talk is up next, and I think, well, it's your beamline, Kuda, as well. You will benefit the most in terms of the coherent flux. So it's kind of exploiting that for kind of the tychographic imaging and pushing that forward. So, if we'll be able to do things much faster, reaching higher resolution. So I think that's where the tychography and the in situ really comes into play.
Yeah. Well, thank you very much, Julia. So I think we'll move on to the next speaker. Our next speaker is Dr. Darren Beatty, who is the principal beamline scientist for the I-18 1 beamline.
Yep, thanks, Peter. I will also need sharing access.
Okay.
Please.
Yeah, because I shared my link.
I may have followed. I did register, but I may have followed the wrong link in the end. Sorry.
Yeah, it's all right. I think Lawrence.
Got it. He's got it.
Okay, thanks.
Thanks very much.
Kuda?
Yes.
Okay, can you see this okay?
Yes, we can.
Kuda, there's always a question in the chat box. Please always take notes. Yeah.
Okay.
Okay, good. Then yeah, as Kuda said, so thanks for putting this together and for the invitation. I'll try to be brief to keep the time, so do bear with me. And I'll give you a quick overview of I-13-1, which is, as Julie said, the coherence beamline, a diamond light source built to exploit everything to do with coherence. I'll give you an overview of what we can do with a focus though on the coherent imaging techniques. So we are operating the hard X-ray regime, somewhere between 7 and 20 keV, optimized at around 10, and dedicated to multi-scale and multimodal imaging overall, again, based on coherent imaging. So nanotomography is our core technique, I would say, that we're trying to image in 3D, making use of these hard X-rays which can penetrate material whilst exploiting tychography and other techniques to extract sensitivity from this interaction. Then strain mapping as well. So if you take, rather than transmission and looking at electron density, if you take a Bragg reflection, you can look at the atomic dislocations on so many materials in 3D at high resolution too. Because we're a kind of nanoprobe, scanning probe, beamline, we can also do elemental mapping on top, so sort of incoherent imaging as a kind of secondary signal, if you like, things like fluorescence and potentially XRD as well. And then one thing that we're very keen to do in general is to develop new methods and play with what you can do with coherent light. Beamline is a long beamline. I won't go through this in too much detail because no time, but pretty standard layout, more or less. We use zone plates for our collection optic. That's one big difference from other similar beamlines, I would say. Yep, zone plates, 6-axis sample stack, so we can do all our rotations and a piezometer for scanning, and we can tilt to Bragg angles and so on and so forth. And then we have a flight tube, which can go to different distances for the transmission signal, plus a robot arm, which you can't see yet here, for holding the Bragg detector. So multi-scale, yes, so overlapping, as Julia mentioned about the group, we can overlap with the full field microscopes by being able to do sort of micro CT as a feature, not optimized, but we can do this. So we can take samples which are suitable for those instruments, we can image them, and then we can start to drill down the length scales to do kind of low mag tychography and near field tychography, and then also the core method, which is this high resolution tychography pushing down to the nanometer length scales. Okay, and we can overlap that then with multimodality. In this case, the fluorescence map, you can scan over your sample and augment on top of it the fluorescence signal for elemental information. So coherent imaging, what is it? For those who don't know about it, you think about a microscope system, you can have your sample, you hit it with some illumination that will propagate to a lens. That lens will form an image on a detector downstream. That is great, but it is limited in two main ways. One is that you're limited in resolution by the lens system. So there are aberrations when you make lenses, and they are limited in their capability eventually. And also that the detector is recording the intensity only. So it doesn't, it's not sensitive to phase change within the sample. Okay, so yeah, you lose half the signal basically. So for weaker contrast samples, such as biological samples and biological tissues, this technique can struggle. There are ways with Zernicke to get around this, but I'll come on to show you why CDI is very strong in this area. What we do is we remove the lens. Okay, so that's no longer part of our imaging process. We put the detector in the plane of the lens and record directly a scatter pattern in intensity. And what we need to do is to invert this diffraction pattern to solve for what the unknown object must be. And given certain conditions, which I won't go into in too much detail, you can come together with a data set which is well constrained, and by applying a priori information about the wavelength and so on of the light, you can solve for what object must have caused this scatter. Okay, so it becomes a computational imaging technique, very heavy on computation, but very flexible in its instrumentation. And here you can see the first demonstration of this back in 2007 with John Rodenberg, the Swiss light source, and here's an example of the beam scanning over the sample. And now this is where we start to show the resolution going beyond that of the probe. So you see here we operate in a defocus mode, so the illumination is a few microns, and we scan that over the sample with overlapping positions, so we get very redundant data. On the right, we collect these diffraction points. That's the measurement that we are making, and what we end up doing is putting it through this algorithm, as I mentioned, constraining between measured data and previous sort of a priori information, knowledge about the illumination and the wavelength, etc., the physics of the whole thing. And that allows us then to unlock ultimate resolution images, so we can then go out to the diffraction limit in principle. There is issues of stability to overcome and coherence, but we can basically drill down to the highest resolution images that you can obtain are done currently with tychography. Okay, so sub 50 nanometers in this case. The world record is currently about 4. And just to reiterate once again, sorry, I've got a few slides on this topic. Essentially, it comes down to focusing your illumination onto your sample, scanning your sample through that beam, recording at overlapping positions, recording for each position a coherent diffraction pattern, so you get the nice interference going on. And that allows you, because you're measuring a coherent diffraction pattern that relates to the underlying wave nature of the beam, okay, that allows you to do wave propagation back and forth and fit that to a physical model of your measurement and refine that global problem to pop out the unknown object. Okay, so it's basically a big refinement of a digital twin of your experiment, essentially. Now, tomography can be appended to this, so that's how we get the 2D images, and that's all nice. We can then rotate the sample to a series of angles, just as with regular tomography. That allows then to get very high resolution, so-called Tycho tomography. And this was the first demonstration at the Swiss Light Source a number of years ago. At I-13-1, we've been pushing for making these techniques more available to users and to real-world applications. So we pushed for increasing the speed of these techniques. And so this was an example now from a few years ago where we managed to get the scanning times down to around 6 hours for a small sample. This is an NMC material. And so we're able to motorize then the charging process. And in one beam time, we were able to get through several states of charge and observe the cracking of this material as it was being charged sort of in situ, which was a big breakthrough for us at the time. But since we moved on quite a bit, so now we have become sort of world leaders in scanning speeds. And so we've been pushing for how can we really get rid of all overheads and come in line with full field imaging. This has led us down the route of getting to about 45 minutes for tomography in this case, for 3D now. Okay, so we can take a 3D data set in 45 minutes. That allows us to sweep through energy, or you could cycle the heat, or you could do any kind of operando measurement on your sample. Here it's a kind of Zane scan. And so we can then get a 3-dimensional kind of Tycho Zanes now within a day, which means within a beam time of 5 days, you can start to observe the state of charge change in these materials. And so this is just a result from a year or so ago, just now in preparation for publication. And you start to see within these secondary particles of NMC, the oxidation state changing from nickel 2+ to 3+. And what's very interesting is how those nickel 3+ features are forming. It was thought they may be coating the sample to prevent lithiation. Actually, they're in layers, it seems. And so this is really unraveling some mysteries around how these elements degrade chemically as well as previously structurally. The other side of the coin, when you try to go to higher speed, is to look at larger volumes, not just to do in situ. And for that, biology is a big driver. I mentioned that being able to observe low contrast samples is a big benefit for us. And so here we were looking at a plastic physical phantom, actually of brain tissue, rather than sort of using up too many mice in the meantime. And so we were able to image, though, 100 sort of micron cubed of material in only 7 hours. Resolutions were limited by the photons available to us at the beamline. We're not upgraded yet, but you can already see that we could observe the key structures that were in these materials, in particular linking up with MRI. So these materials are being scanned and used for modeling of the MRI systems. And here we can start to give them high resolution validity to the MRI models. Okay, so in this case, we can start to see these tubular structures within the material. Pushing on a little bit further than that, so we're limited by the motion and the flux, essentially. So the scanning motors are one limitation, and also the flux. So we went to a pink beam geometry where we could exploit more of the partial coherence, and we were able to do sort of very fast, small samples now, half-a-second imaging, so 6 minutes for one of these Tycho tomographies, and for the bioimaging now, 1/4 millimeter cubed, starting to get down to 9 hours. So we're getting towards kind of relevant volumes for biological tissues. Okay, the millimeter cubed is a kind of a global goal because that's the microcircuit size of a brain structure. I might skip over this slightly just to say how the other techniques link in. So this was an example from a long time ago with micro CT linking into the fluorescence, where we're able to kind of correlate form and chemistry to understand how these particles from the Fukushima disaster were formed and landed on the outside of the site. And by looking at the structures in the bubbles, you could tell how quickly they were heated and cooled down, which tells you about the conditions they were in. And then the elemental composition tells you from where in the reactor core they would have come from. And they were starting to use this to kind of back engineer the disaster and understand the conditions in various places within the reactor core. Another example of using this modality of XRD and XRF together is understanding ancient Greek medicines and kind of heritage science. And so we're understanding here how different materials ended up inside these medicines and were they really a poison or were they just contamination from afterwards. And that depends on whether they are formed together or whether they are disconnected. So we're able to use XRD to look at the kind of the compounds involved, and then looking separately with XRF, we were able to identify where the lead and the iron was overlaid, and where they correlate, they are manufactured, and where they are not correlating, they are clearly picked up sort of after the fact. And so they're unraveling again these kind of mysteries now, but in heritage science. Very quickly, I'll also touch on Bragg CDI. This is another way of exploiting coherence rather than looking in the transmission modality. If you have a distribution of crystals, then you can look in transmission using these techniques as such. But if you put the detector now into a Bragg geometry, you can see a whole series of crystals hitting this powder ring. And if we go to coherent mode and we zoom in to one of these crystals, we can perform these tychographic style reconstructions on a single Bragg peak. And that gives access then to the deviation from that Bragg condition within that voxel. So you start to get a strain map within your crystal. And now, why does that matter? That matters for many reasons. And this example here is of solar cells, which are made up of one way of making these is with perovskite crystals. And so we had a user group from Cambridge that came to do this Bragg CDI imaging at the beamline, and were able to do in situ by probing this with a laser to see how these materials perform and degrade under stimulus, basically. Okay, so here's a setup of the beamline. Beam coming from right to left. So we have various cameras to help align the sample. The flight tube then in yellow to the left is where you go to get the small angle scattering signal onto the detector, and a little laser coupler was set up to point at the sample in the appropriate way. This was then, detector moved with the robot arms, as you can see on the left now, into the Bragg condition, and the measurements were made. This is a bit of a schematic of how that sample was looking, and also the if you look here, you see the diffraction pattern in this case, and you rock through this Bragg condition, recording a series of these similar coherent diffraction patterns, and allows you to basically recover again a 3D volume where that volume relates to the strain. Okay, and we're able to basically track how dislocations are forming and mobilizing as a function of light intensity through these measurements. I think I'm overrunning time, so I will jump to the end and just say thanks to everybody involved. This is not an exhaustive list neither, but these people are certainly involved, plus many others, all the beamline team, and indeed the wider imaging group for various collaborations. So thanks very much.
Thank you very much, Darren. Very interesting talk. Are there any questions? In the chat, there are none. Okay, so if there are no questions, well, thank you very much, Darren.
Yeah,
I
thanks
think since we're way behind time,
yes,
we'll move on to the next speaker. Our next speaker is the principal beamline scientist for the I-12 beamline, Dr. Genoveva Beck. Must be pronouncing that the wrong way.
Okay, it's you are almost okay, Kuda. It's Berka. Yes. Can I share my screen?
Yes, you can.
Okay. Can you see my screen now?
Yes, we can see it.
Okay, thank you very much. So,
but the slides are not yet in presentation mode on our side. Yeah. Awesome.
Now, can you see?
Yes.
Okay, perfect. Okay, good. So thank you. I'm Genevieve Berke from I12 Beamline, and I'll give a short introduction about I12 Beamline and few science examples, recent examples, and also some old examples. So I12, the Joint Engineering Environment and Processing Beamline at the Diamond Light Source, was designed for research primarily in the fields of material science, engineering science, medical, and environmental studies. The beamline is one of the oldest from Diamond, so it's operational since April 2009. And we are working with high energy, between 50 and 150 kV. In fact, we are the only beamline at Diamond with so high energy. We are working in both modes, white beam and monochromatic. We have a large beam size for X-ray imaging, from 50 by 15 millimeter in experimental hatch 1 up to 100 by 30 in experimental hatch 2. We are doing not only imaging, we are doing imaging, diffraction, scattering, and recently we implemented also fluorescence applications. We have in situ environments, our own sample environment, and I will give 2 examples in my talk. And also users can bring their own sample environments for in situ measurements, temperature, chemical processing, and any type of experiments for chemistry or engineering applications. We have imaging cameras, fast camera and standard PCO detector for standard measurements. We have diffraction detector and also Hexitech detector for fluorescence applications. We have a large area detector for diffraction, and we can move the detectors from one hatch to the other one. We can't run both hatches in parallel. So if we are doing measurements in EH1, then we can do offline measurements in EH2. Or if we run experiments in EH2, then EH1 is completely closed because the beam is passing through EH1. Go the next slide. So we are covering a microscopic and microstructure, let's say, a range of measurements. For imaging and for diffraction and scattering, we can go to atomic structure. And we can go deep to get an idea about what kind of power, let's say, we have on I12 in terms of energy. We can go deep up to 3 centimeters of steel, not so deep like neutron diffraction, but it's deeper than other beamlines with lower energy than I12. So we are doing applications in engineering and material science, from creep, fatigue, damage, failure, strain, texture, phase transformation, crystal growth, recrystallization. Recently, we started to do a little bit more applications in chemical engineering with colleagues from Birmingham University or Sheffield University. These are in situ or non-situ applications. Earth and environment science, including paleontology, cultural heritage, and also agriculture applications, and the biomedical imaging. We can do in situ applications or non-situ applications, for example, bone under load, implanted tissue, or soft tissue. Experimental hatch 1 is a multi-purpose hatch. We are doing measurements on small and medium-sized samples under static and dynamic conditions. And here you can see a setup in the hatch with a tomography stage installed on our standard stage. We can mount samples up to 50 kilograms for tomography or equipment up to 50 kilograms. So we can rotate this stage. And we have in transmission mode diffraction detector placed, and also this setup is for imaging camera with 4 different modules. So we can go from 1.3 micrometer pixel size with field of view of 3.3 by 2.8 millimeter to up to 18.53 micrometer for field of view of 50 by 12 millimeter in EH1. The main aspect is that we can use these different techniques, imaging or diffraction, without sample realignment. So the sample, for example, same group of users can do imaging and diffraction. They are they are not doing this same time. So we have to move into the imaging position or diffraction position. So we have some rails, and when automatic, the detectors will be moved left or right, and the sample will be on the same position on this stage. Second experimental hatch is dedicated mainly for large samples or very large equipment, in situ or non-situ, similar to EH1. We have a larger beam size. We can go up to 100 millimeter horizontal beam size, height 12 millimeters. So this hatch also allows us for offline measurements with our equipment, and we can also set up experiments here and then move equipment in H1 or continue measurements here. We have this large sample stage up to 2 tons we can mount, and also this is a tomography stage, and we can do measurements for large samples. I'll show you information about sample environment available on I12 is on our webpage, which is up to date, and you can find all kind of information, including the detectors, setup, resolution, techniques available, example of science we are doing on I12, and also our own equipment. In my talk today, I want to highlight 2 specific sample environment we have on I12. First one is Instron rig. It's a large rig for in situ compression and also for tensile measurements on I12. Because it's so large, it's placed on EH2 on our large sample stage. And with this detector, with this Instron rig, we can do measurements not only in diffraction mode, but also in imaging mode, limited angle tomography, so we can combine imaging and diffraction. So here you can see, for example, we move a diffraction detector from EH1 to EH2, and we collected some diffraction patterns for the same sample in the tensile mode. And also we can do imaging because we have a large field of view camera, but also we can move a PCO detector from EH1 to EH2, and we can do limited angle tomography because we can't do a proper tomography 180 degree. We have these pillars of Instron rigs, so that means we have to do limited angle tomography, but we can reconstruct the data, and there is no issue in data analysis. The second sample environment I want to highlight on I12 is this heating furnace. Was built in collaboration with Oxford University by a PhD student. And we can do, it's used for in situ chemical experiments, not only for diffraction, but also for imaging. So we can rotate the sample inside of equipment because the sample is placed on the tomography stage and it's placed on a stick, and then we can rotate the sample. It's not quite often used, but recently we started to reuse it again with colleagues from University of Manchester and colleagues from University of Toronto, Canada. I want to show only a couple of examples. I don't want to cover all kind of research you are doing on I12 because it's a very wide research area. First one is biomedical engineering. So here it's an example of tomography of a bone with titanium implant under compression loading. So we have a compression cell, Debon rig on I12, so we can do in situ measurements, compression, here in this case, compression test of a goat bone. Also for fast, speaking about fast measurements, we can do applications in engineering. So this is an example of high-speed tomography, observation of a changing structure of metals during processing operations. So in this case, a special experimental heat and stress unit was installed for applying tension or compression to heated metal to study tearing of steel at 850 degrees. And the extrusion of semi-solid aluminum copper alloy. The equipment was user equipment and was tested on I12 a few years ago. The development of internal voids in the hot tearing of steel can be observed directly during the process, and the interaction of solid particles leading to non-uniform concentration of extruded metal also can be seen. Here we have from the same experiment 2D vertical cross sections from tomographs show solidification defects in the upper half of a sample. And a second cluster of the image forms further down the sample where there is both porosity and inclusions. And here you can see 3D rendering showing necking and damage connecting to the surface of a sample. In the recent years, we started collaboration with ICE's neutron source. So as you may know, neutrons are complementary to X-rays. So what you can see with X-rays, you can see with neutrons. What you can see with neutrons, you can see with X-rays. So this is an example of correlative imaging between neutron and X-ray. X-ray measurements done on I-12, neutron measurements done at ICES on IMAT beamline. So here, for example, on this movie, you can see cross sections through these scraps with X-ray measurements, and we can see some nicely cracks and other features because of resolution. But in this movie, you can see features, hydrogenous materials deposited into the fossils with neutron imaging. And this is an example of overlapped neutron versus X-ray data of fossil ammonite from Jurassic, very old sample, measured at both facilities using same type of software for data analysis and for segmentation. We pushed a little bit further, collaboration with ICES, so we are doing also some neutron versus X-ray imaging on soil plant systems. So this is an example of lupin seeds. So what you can see here on the left-hand side, it's, sorry, my screen is quite bright. These are slices through X-ray data collected on I-12. So it was an aluminum tube, 2 centimeter width. We did a double field of view because the field of view was smaller and I wanted to go for a high resolution. So we have soil distribution, grains and everything with high resolution on I-12. On the right-hand side, we can see neutron slices. So resolution is not so great, but I'm trying to go back to the movie. We can see this bright area, which in fact are cross sections through the roots of a lupin. And this is overlapped neutron versus X-rays. So while neutrons are sensitive to light elements, including water, which is bright to neutrons, X-ray can see very nicely soil distributions and grains. Another example is a collaboration with colleagues from Uppsala University. We did X-ray radiography here on I-12 and then neutron radiography, and also we continue with neutron tomography versus X-ray tomography. So we managed to correlate neutron with X-ray data, and we were able to see different features in our sample. Was a composite soil material with different aggregates and plant seeds and plastics and quartz sand. This is the last highlight of our beamline applications in paleontology. So we recently published 2 papers with collaborators, external collaborators in Nature. So when we work together with colleagues from PSI or ESRF, exploring potential applications in different areas of research. Also, we continue applications in bones, archaeological bones, neutron with X-rays, and some applications in agriculture, pellets with colleagues from not only from ICES, but also from laser facility, exploring Raman spectroscopy on life sciences applications. So because I mentioned about X-ray and neutrons, I want to show you an example how powerful are X-rays. So we can easily penetrate lead, lead with neutron imaging. But on X-ray, lead is completely opaque because it's used as shielding. So from here, the idea of using neutrons versus X-rays, and because I-12 is very similar to IMAT beamline from ICES in terms of field of view and also capabilities of different applications, I think this is a good idea to look at our facilities and also exploring our capabilities. Thank you very much.
Thank you very much, Genoveva. That was a very, very interesting talk. Just to mention that we actually have one of the iconic paleontological specimens from South Africa called Littlefoot, which was also where they did tomography at I-12, and then they went to ICES to also do tomography with neutrons. I don't think, is there anyone with questions? Okay, if there are no questions, then I think we'll move on to the next speaker. Our next speaker is Dr. Christoph Rau, who is the principal beamline scientist of I-13-2 beamline. Christoph?
Yes, I just try to find where to share.
Okay.
You can hear me at least, no?
Yes, we can hear you.
Okay, where's the sharing? Here, okay. Okay, my name is Christopher. I work for Diamond Light Source, and I'm talking today about micro nano imaging with the Diamond I-13-2 beamline. And in this context, the Octopi project, I will explain in a minute what's this about. And to start with, I put at the first slide the first X-ray image taken by Röntgen in 1895. And if you have a close look, you see very well the bone structure and also the wedding ring. But all the other structures are much more unclear, and it's unclear also whether that's Röntgen's wife, the hand, how far she wears the ring. Is it really all the way down the finger? And that's, I will elaborate this a bit more further down the line. So to start, to explain you about the beamline, we heard first the talk from Darren about the coherence beamline I-13-1, which achieves a resolution of less than 50 nanometer. We are working a bit less resolution in the micrometer to 50 nanometer range, with the sample size from 10 millimeter to 50 micrometer, roughly, a resolution of a micron to 30, 50 nanometer. And we can do full 3D tomography within a couple of minutes down to seconds. And anything which is small, we can record rapidly. So to explain first a little bit about our standard method, which is called phase contrast imaging. So we all know what I showed on the first slide, the hand, the absorption imaging, here the shadow image of my colleague, Steve. The sun is shining from very far away, and then the shadow projection of the sun is then projected on this screen, and you can see his shadow image on the screen of the window. And that's absorption. In contrast to this refraction, here the swimming pool, you see the swimming pool has clear water. The water doesn't absorb anything. But because of the refraction, you see at the bottom of the swimming pool patterns. And again, that's related to the fact that the sun is very far away. and that the water has a refraction index different to 1. Question is whether this is valid for X-rays also. The reality is that in general for imaging we observe both absorption and refraction, and that's represented by this image here. You see the shadow image of the lady here, and at the bottom at the same time the deformation of the shape, and again the brightness due to refraction. And the question is now whether this is valid also for X-rays. For a long time, it was thought that for X-rays, that's not possible because the refractive index is very close to 1, while for water it's very different to 1. But it turns out the refractive index is slightly different to 1, and that's sufficient for this type of experiments. And to explain you the setup, so what you see, our X-ray source is about 200 meters away. And then we have the detector on a sample stage. That's what you see on the left side. And on the right side is the detector. And the distance between the detector and the sample can be changed, like the depth. Well, that would correspond now to the depth of the swimming pool, and by changing the distance between the sample and the detector, we can play with the fringes we observe at the bottom of the swimming pool. So to say, we can play with the contrast. And I demonstrate you this in a second. So what you see here is a sample of 2 crossed hairs, and the distance between the 2 crossed hairs and the detector is very small, just 2 centimeters, and you can barely see these 2 hairs. So there's a little bit of difference in absorption, but it's very hard to see these hairs. But when you're increasing now the distance between detector and sample, you see that the edge of the sample is much enhanced, and the 2 hairs become more and more apparent and have a very strong contrast at the end of the range of sample detector distance. And that's what we are using for most imaging experiments. So to show you some examples, the quality of imaging we can achieve, you see here the reconstructed slice of a mouse knee. And I would like you to pay attention at all the details you can see in comparison to the first image I showed you. You can see all the soft tissue, you can see the bone, you can see any kind of cartilage into great detail. And that's the whole strength of this imaging method. And I'll show you now a couple of examples of applications. Here is first the study of a knee. Knee put under stress, a mouse knee is put into a tension rig, and tension is applied then. And while this tension is applied, we record tomographic scans. And that's the result of the scan. So we are zooming through the knee now. And what you see on the right side is then the knee under different load conditions. And from this, you can deduct then features like the stress which is happening in the cartilage of a knee, and that has been studied for the deformation of young joints and to investigate osteoarthritic joint stiffness. And that's a very typical type of studies we are doing, where you have at the same time looking into very small features and learning the properties under dynamic conditions. Another example of this kind of study is related to water management, and here biochars. And that's a very important topic because the access to clean water for everybody in the world is something quite important, especially important in the future. That's not the case everywhere. Not everybody has access to clean water, so you need filter material, and the accessibility to this filter material is also limited. So how to get around this? And the idea is nuts. They're shown here on the picture. And the idea is to transform the nut shell into material which is usable for filtering to generate microporous materials. So what we're doing is, and that's in collaboration with our colleague Roberto, we fill into a capillary here the nut material, the sample, and then the sample gets heated up by a heater, and we observe then the formation of this microporous material during the heating process. And at a given distance, we place it in the detector. And the carbonization process is happening by heating. That's the investigator, Roberto, and that's the kind of sample environment they have been producing, where the nut shells are just inside these small quartz capillaries. And here you can see now what happens with the nut shell during the heating processes. You see the formation of the micropores, while at the same time the shells are collapsing. And what's interesting now is how you optimize the formation of the microporous material. And the idea is now to find a kind of what I would call a cooking recipe, how to prepare the samples, how to heat them up, what's the right heating ramp, and how to prepare them, especially how to wash them. Because what was found that the morphology of the walnut shells changes with temperature slowly, and at a given temperature of around 500 degrees Celsius, about a little bit more than 20% of porosity is achieved for this nut material. So what's happening now when we wash the material? We remove metals, and that has a huge impact in the formation of pores. So if we wash the nuts before heating, we found out that suddenly we achieve a porosity of over 30%. So that's quite important, and that's a very typical kind of research we're doing. And that we do not only on the micro length scale, and that's now the relation to multi-scale imaging and the so-called Octopi project, which is about multi-scale imaging. We see then when we apply different imaging methods, I will not explain all of them in detail, but only so much. Microtomography I spoke about. We have a X-ray microscope, which works like a visible light microscope. From the principles, we can achieve 50 to 100 nanometer resolution. And then Darren spoke already about tachography, where ultimate X-ray resolution can be achieved, and this being complemented with electron microscopy. So there's a whole chain of methods to apply it to investigate the properties. Similar on other topics, I will just show in the following a couple of other themes what we are doing. For example, the study of moth wings. Moths have, there are certain specimens of moths which have a particular property that they can absorb sound waves, so they become opaque for their predators, namely bats. Bats send out a sound signal And because of the structure of these specific moths, the sound gets absorbed, and that's related to the structure. And you can see here now the arrangement of the microstructure on this picture, where you can see different types of structures, of this spiky structure, of this in blue more and yellow more like a filament. So different type of structures, and then on a smaller length scale, it has been found that's work with CUDA, that you see here now this nanostructure of these moth wings. All this combined leads to the particular properties of the moth wings. Other things we are doing, we are much interested into the study of insects also. We do what I would call reverse engineering. We measure the structure of eyes, insect eyes, and from that on we can then deduct the optical properties and simulate the field of view of the insects, and about their behavior, how this is related. Here, whether the eyesight of male and female is different for bumblebees, and what has this what's the impact on their behavior. That's a very typical kind of study we are doing. I thought it might be also interesting to know a little bit more about material science. Here we are looking at the dendritic growth of aluminum alloys, and here the interesting thing of the study is that we look at different length scales at the same time with a specific detector system. So the alloy is cooled down, and then you can see on different length scales at the same time how these alloys are formed. So that's also a very typical field of application that we are looking into. And to come towards the end, and in my time also, we are currently improving the productivity of our beamline by high throughput tomography. What we are doing is we employ a robot, and this robot is changing automatically the samples from the sample holder to the sample stage, and then a fully automated tomographic scan is performed. We can run something like 300 samples a day, and in the future even more. And that allows us to record statistically relevant data, large numbers. And what we have to look at now to progress the data analysis. Currently, we are collaborating with the Natural History Museum in London. They are namely Anjali Goswami, and they have something like 4 million samples, so enough for the near future to measure. And that's when we visited them at the Natural History Museum in London and doing one excursion. So at the end, I would like to thank all the people, well, the beamline staff in particular, Shashi, who has been now here for about 10 years, Zian and Carlos joined more recently, and our beamline technician, Tim. They're doing all great work. And of course, thank also all our neighbors and all other people who help and support the beamline. Yeah, Darren gave a talk earlier at CUDA, Zifan from the neighboring beamline for X-ray optics with Florian and Christian, and the people who are helping day to day with the beamline work, Cass, you, Andy, and all these people. And I thank you for your attention.
Thank you very much, Christoph. That was a very interesting talk. Because we're out of time, we can take one question. Does anyone have a question? Comment?
Yeah, thank you very much. A great presentation. And I just have a comment for most of the speakers to drop their email in the chat box, because some of us, we are working on biomaterials and you polymer materials so as well. So we need such techniques, and it's look very nice to me, so that we can be able to follow it up.
Yeah, you're very much welcome. Yes, yes, please.
Thank you very much. So I think we now go to the last speaker in this session. That will be Dr. Christopher Allen from EPSIC.
Hello. Right, just trying to get my microphone and camera working. Can you hear me, Kuda?
Yes, we can hear you and we
Fantastic.
can see the slides.
Are they in presenter mode or are they
Not yet in presenter
not
mode.
yet in presenter mode? Let's see if I can get that working. There we go. Okay, is that good?
Yeah, that's awesome. Thank you.
Fantastic. Okay, well, thanks very much for the invitation, Kuda, to come and speak. A slight change of speed here, I guess, because I'm going to be talking not about X-ray microscopy, but about electron microscopy. So my name is Chris Allen. I'm a principal electron microscopist at the Electron Physical Sciences Imaging Center, which is a center for aberration-corrected electron microscopy, which is based at Diamond Light Source. And we're a user facility, just like the other X-ray beamlines. But of course, we use X-rays. We use electrons for our imaging, not X-rays. You've heard a bit. I think Christoph mentioned it briefly, as did Genevieve in her talk, about the importance of correlative multimodal imaging to really understand your material over a wide range of length scales. What electrons really excel at is looking at very high resolutions very locally. So we are particularly interested at looking at deviations from perfect crystallographic structure at very high resolutions and at over very small fields of view. And then the reason we're cited at Diamond Light Source is so that this information can then be correlated with the much larger field of view, larger length scale sorts of studies that you've seen already in various talks. Okay, so I'll just give a quick overview of the instrumentation that we have at EPSIC that's available to the user program, and then a few examples of the sorts of science that we will do. So we're very focused on physical sciences, so mostly studies of material systems. We don't really do well. We do very little biological work. There is another center based at Diamond Light Source who focus on electron imaging of biological materials. So our focus is very much physical sciences. We have two aberration corrected instruments. Let's see if I can get my laser pointer working. In our center, two aberration corrected transmission electron microscopes that we've called EO1 and EO2. One of them is set up for spectroscopy. So this has an electron energy loss spectrometer and large solid angle energy dispersive X-ray detectors. And that's for looking primarily for looking at the chemical structure of material systems at atomic resolution. Then our second instrument is an imaging instrument. This has very limited spectroscopic capabilities, but is really optimized for imaging, both in STEM focus probe mode and broad beam TEM illumination across a very wide range of energies. And this instrument is equipped with a variety of different detectors to do some advanced imaging techniques that hopefully I'll have time to get onto a little bit later. Okay, next slide. Okay, we've got a range of in situ capability that can be used on either of our aberration corrected electron microscopes. So we have a gas cell holder to do in situ gas experiments. You can flow gases through over your sample, change the mixture of the gases going over your sample, change the temperature of your sample, and look at any any reactions that happen to be going on. Likewise, a liquid cell holder that's similar to the gas cell holder, but obviously we're using liquid as your medium. We then have heating and cooling holders to enable you to heat the sample up to about 1200 centigrade, and cooling holders that will cool the sample down to liquid nitrogen temperatures. So that's something like 100 Kelvin, just to mix my units there. We also have a biasing holder that enables us to look at functional electronic devices while they're being used, and perhaps how the structure of those devices might change under bias, and an anaerobic transfer holder that enables us to get samples into the microscope without exposing them to air, which is particularly important for our users from the battery community. So over here on the left, then images of some of the holders. These images here, hopefully you can see my laser pointer. This is some platinum nanoparticles. That's a common catalytic material, and these are being imaged at 800 degrees C under about 1 bar pressure of a carbon monoxide oxygen mix. And then on the right here, we've got some 4D STEM measurements, and I'll talk a little bit about 4D STEM later. That's looking at the creating crystallographic orientation maps, again of platinum nanoparticles, but this time under a reducing environment. That's under a hydrogen argon mix, again at about 1 bar and 500 degrees centigrade. So that's the sort of quality of data we can get in the gas cell holder. It is possible to get something close to atomic resolution, as you can see from these images of the platinum and nanoparticles. For the liquid cell, the resolution is degraded because there's a significant amount more scattering as you move through the medium than there is in the gas cell. But the heating, cooling, biasing, and anaerobic transfer, all of those were able to get very high resolution, atomic resolution. Down here in the bottom corner here, this is a picture of a tantalum diselenide film, which is measured at 100 Kelvin. Each of the little white dots is an atom essentially, and the yellow ring here is showing up in the top corner here, we have the power spectrum of this image. That's showing the frequencies that are present in that image, and the yellow ring showing 1 angstrom. So that's giving an indication of the sorts of resolution we can get with our in situ holders. We also have some auxiliary instrumentation to help with sample prep and sample screening. We have a gel gallium fib 4700F that we use for making fib cross sections, both for use on the electron microscopes and also for the X-ray beamlines. In fact, Kuda does a lot of work on this fib with us for his X-ray experiments. We've got an analytical SEM for doing sort of low resolution, tens of nanometer scanning electron microscopy and spectroscopy. And then we've got a glove box which we've modified to enable us to insert our holders in the side of it. So that's mostly for anaerobic transfer. So that's something that we've built in-house. Okay, so that's a brief overview of the equipment. Now then, just to talk a little bit about the sorts of science that we do at EPSC. So our sort of bread and butter, I guess, is atomic resolution imaging. So we're interested in looking at deviations from perfect crystal structure. So this first example in the top left here, this is a piece of work in collaboration with the group of Susie Speller at the University of Oxford, and this is looking at rare earth barium copper oxide materials. So these are high temperature superconductor materials that are used for or are candidates for magnets in fusion reactors. However, when you use these practically in a fusion reactor, when they're radiated with, as inevitably they are, with neutrons in the fusion reactor, their properties very quickly degrade. So they stop being such good superconductors. And when these materials are degraded and they're studied with X-rays, it's very difficult with the X-ray imaging and diffraction to actually see that there's been any change in the material. The irradiated samples look very, very similar. to the pristine samples. However, when we go in with our atomic resolution imaging, we can really see at the local structure, we can see changes in intensity on the atomic column. So each one of these bright dots is an atomic column that tells us actually that what's happening in these materials is we're getting a deficiency we're getting local oxygen vacancies formed when the materials are irradiated with neutrons, and that's causing the breakdown of the superconductivity of these materials. So that's a very an example of an atomic resolution imaging we might be doing in STEM, in ADF STEM. We're getting a bright contrast of our atomic columns, and we can measure quantitatively how many atoms there are in a column from the intensity and the contrast. The other imaging modality that we use very regularly is a TEM imaging. So this is a broad beam flat field illumination, much more like a standard light microscope. And the image formation mechanisms in a TEM image are much more complex than they are in a STEM image, so we don't have that direct correlation between brightness and number of atoms in an atomic column. However, the images, we can take them very fast, and I'll hopefully have time to show you some high-speed imaging later on in the talk. But we use this modality to get relatively large fields of view, and again, to see the atomic structure of materials, and once again, to look at defects, to look at variations from perfect structure. So this is an example of an experiment, the ongoing collaboration we have with the University of Nottingham, where our collaborators deliberately grow defective graphenes. They grow it from a gaseous feedstock that has a particular structure. That means when it's formed, it doesn't form perfect hexagons, but in fact forms lots of defect structures. And hopefully you can see in this image, we've got regions where we've got the perfect six-fold symmetry of the graphene lattice, and then we've got other regions where we have much larger and smaller rings, and these are deliberately introduced in the growth process, and there's a degree of control in the density of these defects, density and type of these defects, depending on the feedstock gas and the temperatures that we form the growth at. And each of these defect locations then is very highly active. It's a very reactive site. So these materials are particularly interesting as potential catalysts for a variety of applications. That's sort of our standard imaging techniques. Moving on then to spectroscopy, we'll perform energy dispersive X-ray spectroscopy and electron energy loss spectroscopy. They're two complementary techniques that give us slightly different information and it's slightly different resolutions. So here, this experiment was actually, again, it was a catalysis experiment. It's looking at a cobalt oxide catalyst that's doped with magnesium, which is a catalyst, common catalyst for Fischer-Tropsch, for the Fischer-Tropsch reaction. And depending on exactly how these catalyst particles are doped with magnesium, they have different activities for the Fischer-Tropsch reaction. And the big question was, what's going on when they perform the chemistry? What's the difference in the chemical structure of these nanoparticles that then causes the difference in the catalytic reaction? So we performed these EDX experiments that gives us these nice elemental maps where the different colors correspond to different elements of two different preparations of these catalysts, one which is what we call the surface dope and the other which is a mixed oxide. And hopefully you can see that in the surface dope samples, the magnesium is primarily at the surface, whereas in the mixed oxide, the magnesium is much more well dispersed across the materials. This is sort of sub-nanometer chemical maps of materials. That's generally what we use the EDX for. The EELS spectra then, we've got in this bottom column, the EELS spectra are equivalent to an X-ray Zanes measurement. So it's a very rich data set from which we can, of course, we can perform elemental maps, we can do elemental imaging with it, but there's a lot more information in these spectra. And oftentimes what we're interested in, what it tells us about the oxidation states of the particular chemical species. So by looking at changes in line shape and shifts in position, we can determine whether the magnesium atom is in a metallic state or what particular oxidation state it's in. And here's various EELS maps at the bottom of that figure. Okay, so that's broadly our relatively standard imaging. This is our bread and butter. We do this imaging of a whole variety of material science samples, whatever anyone can think to bring to us that requires this high resolution spatial and spectral imaging. We've heard a little bit from, as I said, from Genevieve and from Christoph and hopefully other people. I missed the earlier talks from the imaging group about the importance of correlative measurements. A huge number of the users that come to us at EPSIC are also doing X-ray measurements at other beamlines at Diamond and are looking to correlate that very high spatial resolution information we can give them with the broader population level information that's available from the X-ray beamlines. So here's just a couple of quick examples. On the left here's some experiments that were done by a group at UCL across EPSIC with the electron microscopes, but also I-20, which is a scanning hard X-ray beamline, and B07, which is a versatile soft X-ray beamline. This is to study, then again, it's a catalytic experiment. So it's cobalt doped copper oxide in this case, which is used for the oxidation of ammonia. And once again, it's trying to correlate different preparations of particles at different stages of cycling and really understand both structurally from the electron microscopy and chemically from the X-ray measurements, how these particles are changing and how that relates to their catalytic activity. On the right-hand side here, we've got that same data I showed you on the previous slide. For these defective graphene materials, we don't just look at them in the electron microscope, they're also heavily studied with X-rays. So there's an example of photoelectron spectroscopy performed on these materials to understand something about the band structure of the materials, and then NEXAS in order again to understand about the local bonding of these materials. So lots of the work we do is correlative, and there are experiments across beamlines at Diamond and beyond. So at HISIS and other other capabilities here at the Harwell campus. I thought I'd dig up a couple of examples of work we've done with universities from the African continent. These are we've done bits of work actually looking at Diamond at Diamond with universities in South Africa. So one of our very early users actually was from Nelson Mandela University, and they had questions about the structure of nitrogen platelets in natural occurring diamonds. So there are defects in natural occurring diamond that take these platelet forms, and it's been long known that these platelets are. Sorry, we're going to get an interruption. I do apologize. We've just got an announcement going on, so I'm not sure if you can hear it, but I can't hear anything apart from the announcement. So I'll just pause for a second. Okay, but actually what the atomic structure of these platelets was unknown, and it has implications on their optical properties, etc. So we did atomic resolution studies and actually solved the structure of these platelets in natural occurring diamond. Another example then is some work that we did with Somnath at Witwatersrand, and this was trying to understand unusual superconducting behavior in his diamond films, and we looked at them and characterized the grain boundaries in the film and came up with a theory that it was in fact these grain boundaries and reflections at these grain boundaries were actually really dominating the superconductivity of those diamond films. Okay, so I think I've spent quite a lot of time already, so I think I will just try and whiz through quickly my last few slides. What I've done so far is mostly sort of conventional transmission electron microscope imaging, and I think anyone who's familiar at all with electron microscopy will have seen experiments much like those that I've presented many times before. A lot of the work we do now at EPSIC is what's come to be known as 4D STEM. which is a slightly different type of experiment, excuse me, in a 4D STEM experiment, rather than just record a single value for each probe position, for each electron probe position on our sample, which is what we would do in a standard imaging, we actually record the full diffraction pattern at every probe position. So we'll raster scan our electron beam across our sample and record a diffraction pattern at every position. So we end up with this really large data set and rich data set of many thousands or hundreds of thousands of diffraction patterns, which we can then in post-processing analyze. And we can set up these experiments in a variety of ways by changing our convergence semi-angle of our beam. That then changes the sampling in reciprocal space. And also changes the size of our illumination in real space. So if we want to have very high spatial resolution in real space, we have to have a big convergence semi-angle in reciprocal space, and that means that any Bragg, it's very difficult to deconvolve any Bragg reflections in our diffraction patterns. There's a trade-off there, depending on the type of experiment we want to use. So I'll first concentrate or give a few examples of experiments where we have a very small convergence semi-angle. So this enables us to separate the Bragg reflections in diffraction space, but gives us a real space resolution of maybe 1 nanometer or 2 nanometers. So we use these experiments to study typically to study materials that are very sensitive to the electron beam that we can't use any other experiment to study. It enables us to have large fields of views. It's a very automatable experiment, so we can collect very large amounts of data, and these diffraction data sets, very rich data sets. There's lots of information in here. However, it does turn out we end up collecting very large amounts of data, so often hundreds of gigabytes to terabytes every day, and the analysis of this data is very complex and involved. Here's just a quick example of the sorts of analysis that we might do. These are looking at, I've got a few examples here that are all from metal halide perovskite materials. So this particular example is actually a cesium formandinium lead mixed iodide bromine perovskite. And these materials are very, very good photovoltaically. They're very, very good. They've got very high efficiency, but they're also very unstable. They break down very quickly, unfortunately. So they don't last for very long under illumination when they heat up, or just over time. And understanding exactly what makes them unstable is a very important material science question. So we've done a series of experiments with the University of Cambridge to try and understand this. And using these nanobeam diffraction techniques, we can record these diffraction patterns from very localized regions. These diffraction patterns would have been recorded from about maybe 1 or 2 nanometer area of the sample. And then by analyzing these diffraction patterns, we can actually pick out the atomic structure of the material. So this on the right here, this is actually the standard cubic alpha phase of the perovskite, which is very photoactive but also unstable. And by adjusting the concentrations of the iodine to the bromine in the sample, you can actually induce a different phase in the material, which is this tetragonal structure that's shown in D here, in which we have this octahedral tilting of the halide sites, the small red dots here. And this octahedral tilting actually turns out it really stabilizes the material without compromising on the photovoltaic properties. This is a very this is a very robust phase. So this was some of the first information that actually it was this octahedral tilting that stabilized these materials, and now there's a lot of work trying to engineer these particular this particular structure. So that single diffraction pattern, of course, when we take these data sets, we scan the beam across a sample. So we end up with a map, much like these in the bottom. This is changing our bromine concentration across the sample. And then we can then pick out different areas of the sample and perform this analysis on different areas of the sample to understand about the heterogeneity of the sample, how much of which phase appears in which areas of the sample. And that enables us to then perform over relatively large areas. So this map will be over maybe 500 nanometers squared. We can then map out the different phase of the material. Here we're looking at the difference between the gamma phase and the delta phase of this cesium lead iodide across the sample to give us information about that information, then feed back in about how to improve the manufacturing of these materials. Okay, Kuda, I've got maybe another 10 or 15 slides, but I think I'm over time already, so I can wrap up very quickly if we're running out of time.
Yeah, I think it would be great to wrap up.
Yeah, okay. So you've heard a little bit about tychography, so we can do that in electron microscopy as well. And tychography gives us really unprecedented resolutions, but also at relatively low doses. But again, it's large data sets and very complex computer intensive data reconstruction. Okay, so with that, I will just get to my final thank you slide. If my slide deck will let me. Okay, yeah. So just want to say thank you to the EPSIC team. If you want more information, you can, using your favorite search engine, just type in EPSIC Diamond and you'll find our website quite easily. This is my email address. I'm always very happy to hear from anyone who's interested in performing experiments at EPSIC, and a list of all the people's data that I presented in this talk. So thank you very much for your time.
Thank you very much, Chris. That was a very interesting talk. I'm sorry we ran out of time, but I think we'll definitely be calling on your door again. But thank you very much. Are there any questions for Chris? I've checked in the chat. There are no questions. So if there are no questions, well, thank you very much. That was the last speaker from the imaging session. I think I will hand over to Gideon Chinamatira. He's going to be the chair for the paleo session, which is coming up next, paleontology session. Thank you very much.
Thank you very much, Kuda. Thank you, everyone. I hope you can hear me. So without wasting much time, I think let's just move on to the paleontology session. Our first speaker will be Tristan Lafette. He'll be talking about his work on South African dinoflagellates. Over to you, Tristan.
Thank you, Gideon. Can anyone hear me?
Yes, we can hear you.
Awesome. Just let me share my screen.
Yes, you can share your screen.
All right. Now. Can everybody see my screen?
I can see it.
Oh, great. So thank you, everybody. Thank you all for coming today. My name is Tristan Lafferty. I'm an American MSc student studying here at the University of the Witwatersrand in Johannesburg, South Africa. My specialty in research is dinocephalians, specifically their phylogeny or evolutionary relationships. So sort of to begin, for those who probably and most definitely don't know what a dinocephalian is, dinocephalians are a group of non-mammalian therapsids. Therapsids themselves are a group of organisms that would eventually give rise to mammals. So mammals themselves, including us, are therapsids. And these are of the non-mammalian variety. Dinocephalians were some of the first terrestrial organisms to reach a body mass of around a ton. And historically, they've been united as a group by having these very large cranium. Dinocephalian itself is Greek for terrible head. When did they live and where? Is primarily they're found in the region of southern Africa and in Siberia. They lived during the Permian period, which was the last period of the Paleozoic era. The Paleozoic was the era of ancient life, so just before the Mesozoic, or the era of the dinosaurs. In fact, dinocephalians were the first group of non-mammalian therapsids to go completely extinct. The majority of them would soon follow at the very end of the Permian mass extinction about 251 million years ago. That mass extinction itself wiped out nearly 95% of all life on Earth. But Dinocephalians themselves died out about 9 million years before that and before all the other non-mammalian therapsids. The majority of ones that we find in Africa are found in the Karoo in South Africa. And we historically have divided them into two groups. The first is the Ankyosauria. This clade was primarily carnivorous, and they're represented here by the two species we do find in South Africa, Ankylosaurus and Australoceodon. Ankylosaurus itself was in fact the largest terrestrial carnivore that the Earth has seen up until that point. And in fact, it would be the largest carnivore that the Earth would see until the emergence of the dinosaurs some 40 million years later. The second group are the Tapinocephalians, represented here by Tapinocephalus and Struthiocephalus. This group has been divided into two based on sort of, and I don't want to get into the technicalities, but based on these large dome heads or these large duck-billed snout-shaped Dinocephalians. They were also the largest terrestrial herbivores during their day. But as to the relationship with themselves and with ankylosaurs and with other therapsids in general, that is not well understood. Here are 4 phylogenetic trees. I've highlighted in the same color each of the different species, but each species has its own color, and you can see how its relationship has varied in the results of these phylogenetic analyses. And there are several reasons for that, but for those of you who aren't aware, phylogenetic analysis is essentially a character model to help understand evolutionary relationships, because without things like DNA that we just don't have in the fossil record, we have to rely on selecting different traits and characters like 5 fingers or 4, thick head, non-thick head, snout, no snout, that sort of thing. And the reason why Dinocephalians themselves have had difficulty in getting a good consensus on their evolutionary relationship is in fact because of their defining trait. So this is an example. This is Moschops. It's one of the most common Dinocephalians, the herbivorous Tapinocephalian line. And they are known for having an incredibly thick skull. In fact, for Moschops' case, the skull can get up to 10 centimeters thick. That makes it difficult in analyzing certain characters in the brain case, which we paleontologists have hypothesized have more of an honest signal when it comes to giving phylogenetic characters. In the past, this is a 1968 model of a cross-section of a Moschop skull. And what the researcher would have to do is he would take a diamond rock saw and basically cut the skull in half, and he would try to analyze the bones and interpret them from there. But this picture looks a lot nicer than what it actually looked like in the actual photographs. It was kind of a disaster, and he had to go through and interpret what he had to do. So that being said, we have started to make headway in the 21st century. This is, for your information, figure A is an ankylosaur, that large carnivorous Dinocephalians brain case and skull that's been cut in the cross section. But on the right is ankylosaur that has been scanned via CT scans, I believe, at the European Synchrotron facility in Grenoble. And with that, we're able to compare essentially how accurate these 20th century models were. So what Julien Benoit, who made this model, he outlined there in green is the endocast, or the brain of this ankylosaur. And it would have sat in this hollow area in Boonstra's model. The purple is the inner ear canal that Julien also focuses on. And it's these sort of things, the shape of the brain and the structures of the skull itself, that we hypothesize are very good evolutionary signals. Most of this work is done at the European Synchrotron facility, which, thanks to the greater access that we can afford to this place, it gives us a much greater resolution and ability to scan these skulls that a normal CT scanner would simply not be able to do, especially with that 10 centimeter thick Moschop skull. For my own research, what I've been doing, this is especially as I've been analyzing some of these more thicker herbivorous Dinocephalian skulls. So This is specimen AM4950. It's called Moschognathus. It's closely related to that previously mentioned Moschops. It's actually the first non-mammalian therapsid to be scanned at the European synchrotron facility. It was done, I believe, in 2008. And there have been several undergraduate and graduate projects around this particular specimen because of its so well complete. But a lot of that culminated in my research project that I published about 2 months ago, where I basically segmented out every cranial bone and gave it a unique description of it to help understand what. It was essentially the first 3D model of a dinocephalian skull that we analyzed. And what I was able to do was same thing with Julian and that ankylosaur, was to analyze and compare it with previous 20th century diagrams. So this is a Moschop skull, and I've highlighted in color the bones that correlate to my Moschognathus reconstruction. And it shows that in some areas, yes, the 20th century model does have some useful, accurate descriptions. And however, there is also some variation within the two species that I'm able to compare. But apart from comparative studies, we've also been able to study pathology with this animal. So this is the CT cross-section of Moschognathus, and if you can direct your attention to the left side here, is where we can see about a 2 millimeter wide abscess in the frontal bone of this animal. We believe it's an abscess we believe it's not post-mortem deformation because you can see the high degree, this white halo around the abscess. That signifies a higher degree of bone density, which is something we would see when an animal has an injury like this. We would see healing in that area. So we're pretty confident this hole was around when the animal was alive. And therefore, it actually documents one of the oldest brain case injuries in the fossil record of about 260 million years. Now, the reason for this abscess, we simply don't know. Some researchers have hypothesized that tapinocephalians behaved in some sort of social headbutting. That's sort of an explanation for why their skulls were so thick. However, that pathology could simply be something like an infection or even bone cancer, but further research and comparison is needed before we can really understand what sort of pathology we're looking at. Apart from my current research, I'm also working on my second tapinocephalian skull. So this is a currently unassigned specimen that I'm working on for my MSc, BP18152. And with that, I'm able to have the second complete three-dimensional skull of a dinocephalian and able to compare it with my previously worked on Moschognathus, to show what are the differences and the variations of the skull sutures and the brain case anatomy, to see how much variation you get for a phylogenetic analysis. But I kind of want to wrap this up and ask, why does this really matter? Well, for the synchrotron stuff, the Karoo itself is a rich source of fossil records in South Africa and Africa in general. It provides a unique window in time that the rest of the world, in some places except for maybe Russia, give us this window of time before the age of the dinosaurs. So it's fairly unique. Places in South America don't really have this time period. Places in North America don't really have this time period. Australia does not. Europe does not. So South Africa and Africa in general is one of the best places to do this. And this provides sort of a window into the terrestrial world of life before the dinosaurs. And as I wanted to mention, these, of course, are mammal-like reptiles, and they are more closely related to us than any other group of living reptiles alive today. And so, in a sense, their story is a part of our story. And thanks to the marvels of synchrotron technology, we're able to study these animals in a way that we simply could not, and the resources were not available to us here in Africa. I'd like to thank the European Synchrotron Facility for providing the scans for these specimens. And I'd love to thank the African Light Source Conference for giving me a forum to speak about this. And of course, the University of the Witwatersrand, where I'm based at, for providing me with an academic base of operations. Thank you.
Thank you very much, Tristan. I think I'll allow maybe for 1 or 2 questions before we move to the next speaker. If anybody has a question. Okay, I'm assuming there are no questions. Thank you very much, Tristan, for the wonderful presentation. We'll move on to our next presenter. That's going to be Dr. Bailey Marquez. He's going to talk about his research work as well. Thank you very much. Over to you, Bailey.
Thanks, Gideon. I just want to make sure you can hear me.
Yes, we can hear you.
Okay, share. And you can see the screen.
It's just started sharing now. Yes, we can see now.
Okay. Okay, so thanks, Gideon, and thanks everybody for being here. My name is Dr. Bailey Weiss. I'm a postdoctoral researcher at the ESI. My host is Jonah Schwania, and I'm going to tell you about one of the chapters from my PhD that I managed to publish at the end of last year. And yeah, I have the privilege of sharing some of the most beautiful virtual histology I've ever seen, and many people in my field have ever seen. But first, I just want to give you some background about the group of animals that we're looking at. So the Crocodilomorpha is the group of animals that includes modern crocodiles and their extinct relatives. They exhibited a much broader array of lifestyles than their modern semi-aquatic sedentary predator members would lead you to believe. They were completely marine members of this clade. They were completely terrestrial members of this clade that walked upright. They were giant predators. They were armored herbivores that almost looked like tanks. So just because their modern relatives are entirely sedentary and semi-aquatic doesn't mean that the members of the group previously have always been. So the Crocodilomorpha first appeared in the late Triassic, and South Africa and the Stormberg group in particular is an important place for studying the early evolution of the group. Unfortunately, though, the group is fairly rare in the fossil record, and often species are only known from a single specimen. And as you can see, South Africa has an really important an impressive number of specimens of this clade. So this rarity has meant that studying the osteohistology, which is the internal bone structure of animals, and I'll get to why it's important to look at histo a bit later, of ancestors is severely lacking. And as far as we know, a paper that was actually part of my PhD in my first year was the first time that an early branching member of this group of animals was described. However, it was only the tibia. Or the shin bone. Within that context, this is where we meet the crocodiliform Orthosuchus. It is known from multiple specimens, which is important. As I said, they're usually known from only a single one. And importantly for this study, 2 exceptionally preserved specimens that preserve postcrania, or parts of the skeleton other than the skull. However, there is no ways that curators and collection managers would allow me to destructively sample these beautiful specimens, and rightly so. So usually when you do osteohistological analysis, you will physically cut the bone and then grind it down so that light can pass through it, and then under a light microscope look at the bone structure. However, as I said, these are amazing specimens, and the curators and collection managers would not allow me to do that. And so this is where we packed our bags and took Orthosuchus to France. It's the same place that Tristan was telling you about, the ESRF in Grenoble. And this facility allows us to, as I'm sure many of you know, use extremely high-powered X-rays to virtually slice the bones. Of course, we used ESRF tape extensively to ensure that the fossils were very well secured and did not break. You don't want to travel all the way there and to not destructively sample the bone, only to have it fall off the stage while it's spinning. So for this study, we scanned as many limb elements as possible. So 8 different bones from the type specimen, so the specimen that is the namesake of Orthosuchus, as well as another referred specimen was also included. So this diversity of limb bones that we looked at made Orthosuchus one of the best known osteohistologically understood crocodilians, including modern crocs. So it's important to understand what osteohistology is, in case maybe you're not too caught up on it. Osteohistology is the study, like I said, of the bone microstructure, and it allows you to understand various aspects of extinct animals' life history. So you can work out how fast an animal grew by the specific types of bone that it had. You can work out how old it was when it died, which ended up being quite an important part of this study, which I'll get to later. And you can also look at things like how compact the bone is, which is really important for animals that live in aquatic environments where they need more compact bone to help with buoyancy, as it keeps them lower down in the water column. So as you can see, these bones scan really beautifully, almost the same as if you were looking at it underneath a microscope. So these were all scanned at a voxel size of 2.4 micrometers. The predominant bone tissue is lamellar bone with areas of parallel fibered bone, which the important part about that is that it's a slow-growing bone tissue. The bones had between 4 and 9 lags, and a lag is just a line of arrested growth, and that's when the animal goes through a period. Usually, it's a period correlated with winter, so you can count them the same way as you can count tree rings, and you can work out how old the animal is. So there was also an OCL, which is outer circumferential lamellae, which an animal puts down once they've reached skeletal maturity. So they're no longer growing. They've reached their adult body size. We also found small patches of woven bone, which is a fast-growing tissue. This pattern of lamellar bone with patches of woven bone is still found in modern crocodilians. So it just shows that in terms of their bone microanatomy and osteohistology, they haven't changed that much over the course of their evolutionary history. Most of the bones exhibited compact coarse cancellous bone and interstitial bone, which I'll speak on later. So just to focus on a few of the specific bones that we looked at, the femur, due to time constraints during the experiment, we only scanned the femur of the referred specimen to compare with the type, which scanned considerably better. The histology of the two specimens were very similar and allowed us to confirm the previous referral of the specimen as Orthosuchus. The holotype of Orthosuchus has been extensively prepared, and this meant much of the outer cortex has been removed, and we were actually able to speak about this as a point in the paper, that sometimes when you prepare a specimen considerably, you're actually removing really important parts of its anatomy that you might not be able to study once it's been prepared. Interestingly, the radius and ulna are extremely thick-walled, which means they only had a really small cavity in the middle of the bone. They also have large amounts of compact coarse cancellous bone and interstitial bone in the inner cortex. This appears to center the medullary cavity in the section. This pattern, interestingly, is seen in modern digging animals. However, considerably more work is needed to understand the relationship of these tissues in burrowing animals. And we were very hesitant to say that this animal was burrowing, because it's also this kind of structure, really compact bone, is seen in aquatic animals, as you can see on this next slide. So we investigated the microanatomy, comparing the bones to other microanatomy we have collected, and those found in the literature. And we found a CDI, which just means how thick the bone wall is. So the actual bone compared to the spongy bone is just a ratio of how thick the bone wall is. And you can see that Orthosuchus is about halfway between another South African crocodile called Latagosuchus, which was definitely an extremely erect postured animal that was definitely running on land. And a modern alligator. You can see it's roughly in between the two. These relatively thick bone walls possibly indicate some form of aquaticness in Orthosuchus, However, as I mentioned earlier, aspects of bone tissues could also indicate a more digging lifestyle, but far more research is needed to investigate the differences between those two different lifestyles. So before I speak about the growth of Orthosuchus, it's important to take into account the size of these specimens. So here I have roughly scaled the size of the little Orthosuchus that's been following us around to that of a yellow mongoose and a chihuahua for completeness, with the human feet in black there for scale. So you can understand this is a really small animal, and when you think of modern crocodiles, it doesn't correlate very well. So it's better to think of it more as the size of a mongoose. So for comparisons between the two specimens, we used just the femora. The overall growth curves are very similar, as you can see. By measuring each of those lines that I was speaking about, the lags, we could estimate the body mass of each growth season. Using this, we were able to show that Orthosuchus had an estimated yearling mass of 215 grams, which is tiny, and a total adult body mass of 800 to 1,200 grams, so about a kilogram, with both specimens having a very similar body size when they died. Yeah. So when looking at the graph of body mass added per year, you can see that both specimens had a maximum yearly body mass increase of about 360 grams. However, in this graph, you can see the largest difference between the two specimens, which is that the specimen that's known as 4242, which was the referred one, appeared to reach a rough adult size a year before. So yeah, there we go. A year before the holotype, adding another 300 grams in that season. However, the spacing between the lags in 4242 is greater than the holotype, meaning they died at similar sizes, despite the fact that the one became an adult a year before the other one. This graph shows the lag circumference of each element, showing the larger femora having the largest first growth mark, which you would expect because it's the largest bone. And for the exception of the radius and ulna, all the bones grow at a relatively equal pace. These bars display the scaled circumference of each lag to that of the final lag. So it's very similar to the previous one, it's just as a percentage of that bone's final size. Here you can see the radius and ulna have a relatively large first growth, being over 60% the size of the final one, while the fibula grows relatively evenly over the course of the growing years and preserves the most amount of lags. This shows that all lag measurement. This graph shows all lag measurements of the limb elements of the holotype. The humerus and femur appear to grow similarly. The tibia and fibula appear to grow similar as well. What is noteworthy is that the radius and ulna appear to grow with negative allometry. So the rest of the bones grow faster than them, so they almost look like they decrease in size relative to the rest of the body. And what was very interesting about this finding was that the slower growing forearm, the radius and ulna, has been reported in modern alligators. So the animal, the life history of this animal and the way it grew seems to be very similar to modern alligator, and just shows how far back this all started evolving. So I hope this research into the growth of early branching members of this fascinating group of animals shows just how important it is to study the osteohistology of animals to better understand their lifestyles and ecology. And what's really important, especially to this conference, is that this would be basically completely impossible without a synchrotron, the synchrotron scans that we were able to get. It's impossible. Well, at least it's generally not possible to do this with a lab-based CT scanner. I think there's some newer models that potentially are able to get to this voxel size and to this level of contrast, but at least not the ones that I have access to. And the contrast that the ESRF and the extremely brilliant light source was able to give us was second to none, and without it, the study wouldn't have been possible. So through this, we can confirm that Orthosuchus was a small-bodied adult with a body mass up to about 1.2 kgs, making it one of the smallest reptiles of its time. And as I said, this study has been published. It was published in a special issue of the Journal of Anatomy. Yeah, so if you want to find out more, you can look it up. I just want to thank my co-authors and to the funders and the institutions as well as collection staff. So thanks.
Thank you very much, Bailey. I'll open this time for questions.
I have a question.
Yes. Yes, go ahead.
So I'm wondering if it's possible to look at certain minerals in the bones and to make some comment about, maybe why the animal grew extinct. For example, let's say if or it could just compare the comparative molecular anatomy of the animal. So if you looked at one of the samples that you were looking at and a crocodile today, could you say that, well, the animal today has calcium, more calcium, and the animals from a long time ago don't, and maybe they lost the ability to assimilate calcium, and that's why they grew extinct or something like that.
I believe it is possible. I think at the moment most of that kind of work is done using isotopes. But I think it might be possible to look at, but I think you need quite a small sample. Yeah, so I'm not entirely sure if I can answer your question thoroughly. Gideon and Kuda might be better ones to answer your question.
Sorry, what was the question again?
I was wondering if there is a big difference in the amount of certain heavy atoms in the bones of animals from antiquity to today. That if the animal had less calcium in their bones, and that might help explain why they went extinct, for example, because their bones are not soft and they were or their bones were soft and they were easily crushed.
Well, unfortunately, it's something that we cannot do in a lab CT. Detecting the amount of mineral, the presence of minerals, yes, but being able to separate which mineral it is and its contents would need additional imaging methods. I think people who are versed with XRD or any other methods could actually chip in and assist with that. It's something we can't do here, unfortunately. Any other questions? Okay, thank you very much, Bailey.
Thank you.
For the great presentation.
Thanks.
So we'll move on to our last speaker. I was also going to speak on her research work, Miss Reitumetse Sebusi. Over to you, Reitumetse. You can go ahead and start presenting.
Hello, everyone. Can you guys hear me?
Yes, we can hear you.
Okay.
You can share your screen.
Pardon?
You can go ahead and share your screen too.
I'm about to share my screen. Share. Can you guys see my screen?
Yes.
Okay. Okay, I'm gonna start my presentation now. Hello, everyone. My name is Reitumetse Sebusi, and I will be speaking about my honors project, which looked at addressing the head posture of aquasaurs with respect to the lateral semicircular canal orientation. There is a need to understand the significance of head posture because it may unveil some aspects of living and extinct organisms' biology. Head posture has been proven to be significant as it appears to correlate with dietary preferences, as illustrated in the herbivorous dinosaurs in the SUMA 2016 paper, as illustrated here on the slide. Secondly, the head posture can aid in regulation of aerodynamics during flight by maintaining flap control and improving vision through stabilizing the posture of the head, as illustrated by the bird on the upper corner on your right. Thirdly, it helps in respiratory function, where upright posture allows for better airflow. And lastly, it can help in social interactions, where we see upright posture can display a sense of confidence and dominancy, or it can be displayed in as a social behavior, as illustrated in Benoit 2015 as a sense of headbutting. What are we actually speaking about is the lateral semicircular canal. The lateral semicircular canal is one of the 3 semicircular canals of the bony lithoids, which is part of the vestibular system. In vertebrates, these 3 canals are responsible for maintaining and facilitating balance, coordinating locomotory movement, and also spiral orientation. The LSC is responsible in detecting rotational head movement, particularly in the horizontal plane. So one might say it works as a spirit level, where it catches lateral side-to-side head movement. So in theory, the lateral semicircular canal should be more sensitive to the horizontal plane, which brings us to the assumption that has been placed in past literature, which says that the positioning of the lateral semicircular canal, by positioning its latch horizontally, it can be used as a proxy to evaluate the head posture of extinct species. The question here is, does that assumption actually work? And one author who looked at birds, which is a very old paper, looked at the neutral head posture, which can be referred as the normal head posture relative to the lateral semicircular canal plane. And he chose his plane at right angles, which can pose as one of the problems. And he came to conclusive results. However, his sample was very small, and the lateral semicircular canal plane was roughly placed, as it's illustrated here. It was placed 7 degrees horizontally, and he did not use any standardized approach. Another study looks at mammals, and that is by Haller. He looked at the lateral semicircular canal being pinched upwards and about 10 to 30 degrees. And he looked at mammals and only 1 species of birds, as well as he made the same mistake as Dijum by using a small sample size and no standard approach. So studies that actually contradict this study is one by Marugan Logan, the 2013 paper, where he used a morphometric approach to answer the to answer this question, but not really actually addressing it the way we're about to unfold in this study. So he actually concludes by saying that the LSC was not aligned to head posture in birds and crocodile species. And another study was of Benoit, where he looked at mammals, and he has the same contradicting results as Verhoeven. So basically, we're looking at two sides where one is saying it works, the other ones has said it works, the others have said that it works. And mind you that these much more new papers, as for example, Verhoeven and Benoit, they use standardized approach compared to the ones that actually agree with the lateral semicircular canal plane being a proxy that could be used as a proxy. Which brings us to the aims of the study, which is firstly to determine how does head posture compare to head posture and the reconstructed head posture in modern archosaurs, as well as the second aim, which is to investigate whether bird ecology could be reconstructed using head posture inferred from the lateral semicircular canal orientation. The question which I feel like at this point could be like, why birds? Firstly, they haven't been studied properly in terms of imposing this question. They are a very abundant species, which is well represented in zoos, and they have a wide range of body sizes, as illustrated here on the slides, which comes with great variety in head postures, different orientation, and not to mention they are the closest relatives to dinosaurs. So for my methods and materials, a total of 59 species, including 55 birds and 4 outgroups, which total to 1,200 pictures, were collected by one person, which is my supervisor, and all of these animals were zoo animals. These photographs were taken with a camera with a spirit level, and the animals were taken in neutral posture, in lateral view. Neutral posture meaning that the animal was in its natural habitat, not being disturbed, and it wasn't slouching or whatever, it was at rest. And basically the measurements of these head postures were done using the software ImageJ. A total of 228 dry skulls in a form of macro CT scans were obtained from Prof. Roger Benson, and these scans are accessible through the software Morphosource. And a total of over 100 species were presented to me, but only 25 species were used that aligned with the species that was collected from the pictures. So only 25 bony labyrinth segments were segmented using a visor. So in order to have a consistent middle ground, only one person did the measurements, which was myself, and the different planes which I illustrated on the slide were named basically the plane of the lateral semicircular canal was determined visually in the lateral view and corresponded to the horizontal plane. The long axis of the skull was determined as the axis that runs from approximately the tip of the beak under the orbit to the occipital, this axis was determined in order to optimize the alignment with the measurements obtained from the live living pictures or living animals. The angle between the LSC plane and the long axis was referred as the reconstructed cranial orientation. In order to better understand these definitions, the two images show the different planes and illustrate how we are going to be naming them moving forward. To remove the effect of body mass, we used literature. Body mass is found in literature to eliminate the effect of body mass. Secondly, we used a time-calibrated phylogeny tree to remove the effect and the significant effect, the effect of phylogeny. And lastly, I'll be using, I used actually the software R to test correlation between the head postures, using linear regression models, as well to test for ecological behaviors, which are diet, habitat, and locomotion. So this section outlines the study's findings on assessing the LSC as a reliable indicator for reconstructing head posture and investigating whether head posture can provide insight into ecological traits in aquasaurs. So the first variable that we looked at was whether these components actually, or these groups, have a phylogenetic signal. And we tested that, and we found that these groups have a strong phylogenetic signal when we looked at the neutral head posture, but there was no phylogenetic signal when looking at the reconstructed cranial orientation. Moving forward, we also used these linear regressions to actually test if these variables were, does the effect of body, is there an effect that body mass implies on neutral head posture and cranial orientation? And based on the p-value, there was no correlation, or it had a non-significant p-value. Which brings us to the main question: is it safe to use the LSC as a proxy? To answer this question, no. As seen with the very low non-significant, with the non-significant p-value and the low r-squared, which implies that you shouldn't use reconstructed cranial orientation in order to infer proxies or reliable predictions of neutral head posture. To test for the ecological variables, we used a non-parametric test, which is the Minute, and the box plots were used, and we found these non-significant p-values. Same goes for the habitat, but I used a different statistical test, which was the Crowell-Willis test, Kruskal-Willis test, and we found non-significant p-values. As well for the locomotion, non-significant p-values. So in conclusion, in conclusion, there's no correlation between head posture and reconstructed cranial orientation. And in the beginning of the study, I kind of hoped that there would be a correlation with the ecological traits, but as the statistical tests have provided, there's no correlation with the ecological traits as well. But in future, we would advocate that further research to explore alternative approach, such as analyzing the head posture during active locomotion. Maybe that would provide better correlations and provide a more study where you would want positive results, I guess. But so active head posture might give us new and different correlations. Or we must focus in integrating the LSC morphology with other cranial features, including brain case sizes. And yeah, thank you. I would like to acknowledge my supervisors, the ESI, as well as my funding bodies. Thank you.
Thank you very much, Ritumetse. Do we have any questions from the floor? Going once, going twice. I see there's a hand up from the host. Is it a question?
That's from before. Sorry.
Oh, okay. Okay, no problem. All right, if there are no questions, I would like to thank you for being part and parcel of the session. I hope you learned one or two things and how everyone is working around this synchrotron and tomography imaging. Thank you very much. Over to you, Lawrence. Think you may take over from here.
Okay, thanks. So we have one last session, which is a panel well, not a panel discussion, an open discussion about networking and how does the African light source facilitate sort of networking amongst individuals, amongst facilities, research groups, institutions, organizations. So we can start that after a let's call it a 15-minute break. So let's 15 minutes, we'll start that session. And again, it'll be an open discussion. Thanks.
Pause.
Lawrence, is somebody speaking? Because I don't hear nothing.
We're on a break.
Ah, you have break. Up to what time?
25.
25.
Yep.
In 10 minutes.
10 minutes.
We start. Okay. Thank you.
Ok, on a pris plus de 10 minutes. Acabo de estoy en su teléfono. Non, ça passe quand même. Oui, quelles sont les nouvelles? Quelles sont les nouvelles? Allô, comment vous allez?
Hello.
Oh, quoi, puis? Bon, je te rappelle par notre numéro.
Okay, why don't we go ahead and get started? So for this session, being so late in the day, what we decided to do was give a short presentation, but then open it up as a sort of an open discussion. So let me share my screen and get us started. So I'll start with the slide. So we have this beautiful conference, and we've had it for a number of years now. I guess this is the 7th one, and we had them alternately in person and online. And since the year 2000, we've had it jointly with the African Physical Society, which works out very well. And now we're at a point where we've sort of developed this community of African users and a global community of people interested in working with Africa for a light source on the continent, but also that are open to Africans to do their research now. So there's sort of two major prongs is supporting Africans that are doing research currently, the current generation, and also doing the planning and designing for an eventual synchrotron light source that could manifest in Africa, let's say in 10 years. So the question becomes, how do we sort of grow the community and to allow the community to sort of collaborate with each other and sort of network with each other? So what we have been doing, oops, let me advance the slide, is developing a web portal that is a online community of practice. So a community of practice, online community of practice, is a term of art that you will see a lot in the sociology literature. It is basically what it sounds like it is. It's a web portal that is used to organize and network and collaborate and grow communities around a specific subject. So in our case, it would be light source users. And so there's actually a lot of famous work on this. There's a sociologist at Stanford who, back in 1973, published a paper entitled "The Strength of Weak Ties." So weak ties means that not people that you are totally connected to, but maybe you know them sort of weakly. So you can think of, in the physics world, strong and weak correlation. So the strength of weak ties is kind of like, you can think of how you might know someone who you maybe went to graduate school with 10 or 20 years ago, or even longer. And so it is the basis for a lot of the social networking that we see. So now, the website that we've been developing, and I'm sure all of you have gotten the sort of teaser for this session, comes down to this. So it is possible to create a global online community for light source users that is responsive to multiple domain names, such that each facility's user group can have its own branded portal, but it's all one big user database. And so if you have this website, light source users, facilities and users and other types of organizations can use this platform to connect and collaborate. And this is about what I was talking about. There's this guy, Mark Granovetter, who's a sociologist at Stanford, who came up with the term called weak ties. And they're particularly, he showed that they were very helpful in developing new opportunities and especially job opportunities, which is what he was mainly looking at. There's another sort of central theory to all of this, and in economic sociology, it's called embeddedness. So, like, if you're a light source user, you are in good shape if you're sort of embedded in the community. That is, if you know people and people know you. So your network, and as we probably all know, your network is a very valuable asset. So what we have been developing is a social network for light source users, such that individuals, the facilities themselves, the intergovernmental organizations, because when we talk about large facilities, a lot of times there's a lot of government to government cooperation, and intergovernment organizations are crucial for that. Government agencies themselves, non-government organizations, both for-profit and nonprofit. So this is industry, this is like universities and professional associations, or what we call learned societies. And what you want from an online social networking in a professional standpoint is, of course, you have your individual. So you're on there as an individual. For this particular thing that we've been building, it includes organizations. So not only the facilities, but professional societies, as I said, like the chemistry societies, physical societies, like the African Physical Society. You can do all the great things that you can do on online social networking, collaboration sites. You can have project teams. You can create interest groups. They're generally called social groups. You can have discussions and forums. You can have a library. So, and that is just a collection of documents. So, for instance, if a partner organization, which could be a beamline, which I will show you later, could have in its library all of its users' guides, so that you could read through, how to use and how to interact with the beamline scientist, how to package your samples, what makes for a successful proposal for that beamline, and so on. These days, there are packages to do online courses, and there's a very famous synchrotron light source course that's online that was designed at the Swiss Light Source by Phil Wilmot. It has a collaboration space so that you can work on a document with someone that has version control, so that you don't erase each other's work. An online community of practice will sometimes have a meeting space, so we can embed Zoom, and also a wiki space. So you could imagine a synchrotron light source Wikipedia, where some common concepts are written about there, and could help with some of the training for some of the basic questions that somehow you're supposed to know, but you don't know who to ask. You can go to the synchrotron light source wiki space. So this is what it looks like. This is a sample front page, and this page is, we call it sort of a global light source users online community of practice. And you can get to this page if you go to lightsourceusers.org. All right. Now I mentioned we can make this site responsive to multiple domain names. Now, why that is important to us is because we know that facilities have their own users organizations. And what we wanted to offer through this site is that each each facility's user organization can have their own front page. So we can customize this at will. So you can see from here to here. We changed this header graphic, we changed this logo, and all of this is changeable. And actually the entire design of it is changeable. This is the sort of the one template that we have so far. It's made with a sort of web page template maker called Elementor. And if you are a web designer, every web designer knows how to use Elementor. So when you type in, if an organization joined this website, they could have their own front page. So this is the one for the African light source. This is one for the Caribbean light source. You can see their logo here. Again, I can change this header, can change all these graphics, can change the text, everything. So again, with all these different front pages for all these different light source facilities or light source communities, the reality is it's all one big database. So now, in addition to individuals, what we call partners can have a presence on the website. And there are a lot of different types of partners. So here, what I show is different beamlines. So a facility could have a presence on here as the facility itself, so it's sort of a central account for the facility, but each individual beamline can have its own profile. All right, so these are ones we just made up, but you can see, this could be any given beamline at any given facility. And then when you go in, each individual can sort of have, like, these are my favorite beamlines. So these are my favorite beamlines. And this is what a beamline or partner profile will look like. There would be a front page, which you could make. I didn't really make anything here, but it's just a normal format. It'd be 4 columns, and there will be a large column up here, which I'll show you in the profile I made for myself. There will be an about page, so it'll be about the beamline. Each beamline can have a blog, which might be important for the beamline scientists to sort of update when there's an interesting result from the beamline. As I mentioned before, each beamline could have its own library, which could be a safety guide.
Lawrence, can you use the big screen?
Oh, am I not doing that correctly? Hold on. Is that better?
Yes.
Okay. So this is the library I mentioned. For the activity, you can think of that as, like, I don't know if you've ever been on Facebook. I'm not really a Facebook user, but every time there's something associated with the beamline that one of the users or one of the beamline scientists who's on this site, every time there's an update, it can go into this sort of activity stream or microblog. As the beamline gets more popular, individuals can follow the beamline. So then now you have a little micro community of the beamline followers. And so you can have, each beamline has its own little community of practice. It could be people who work at related beamlines, or a lot of people they use the same technique going to different facilities. I'll come back to groups, but you can create interest groups. This review's actually, I took this picture. This is my admin account. So normally people would not have reviews, so ignore that. And a message center. So a beamline like this, which has a profile, there will be someone who would be, I guess, like the manager of this site from the beamline. And you can send that person messages if you like. So just basically contact the beamline. And again, this is my admin account, so that's the settings would only be there for an account like mine. And in addition to the partners, this is what the page for individuals would look like. So so this is my account here. This is one of the developers, but individuals would have their account, and this is sort of the directory page. Now, if you go into an individual's account, you click on their name. Each individual has a home page. This is the one I created for myself. And I just use some random graphics I got from someplace. So the template that we have in place now, you have basically 4 columns and 1 large graphic area. And we can put more text boxes down. Here we can actually do that on a per user basis. If you know how to use one of the page designers like Elementor or something like that. So you can make your front page look however you want. And then you can go in and make a profile for yourself. So this is basically like a resume. And you can put a little picture in here. So this is kind of a dummy account. But this would be your user. This would be your about. You could talk about, you can list your expertise. So we have a lot of, we have certain expertises that are there, and it's, you could sort of check the box. You can list your affiliation and give your education. So it's basically a CV creator. All right, so that would be your profile. And then if you go across all these different tabs here, this is part of the website that sort of belongs to you. So I mentioned that every user can have a blog. So this tab would be your blog. Every user can have a library, and plus there's a central library, but this would be your library. And on down the road, so this is your network. And I click on that tab and you get these sub tabs. So these are individuals, partners. These will be people who are following you. These are people who you're following. These are people who are following you. There's a separate thing called connections, which is connection is someone that you're following and who is also following you. There might be somebody who you're sort of interested in their work and you're just following them because you find their work interesting. You can have collaboration teams and also your group of partners. And I mentioned what partners are, which are beamlines and organizations. This views, that's for, that's an admin tab that would not be available to most users. I mentioned my partners. So we have a bunch of preloaded partners or sample partners. So this is what my profile will look like. I have a header graphic, and I have a profile image, which should go right there, but that normally is someone's headshot. And so these are the two partners I decided to make my partners, that I'm specifically following. All right. And as you can see here, there's certain partner types. I don't know if you can see these subtabs. They're agencies, they're beamlines, centers and institutes, companies, education and training. So, and then under there's universities and TVET. So training, vocational and education training for companies. or training schools. The facilities themselves could have a presence. Research foundations, intergovernmental organizations, and science organizations. And under here, we would be mostly professional societies. So, for instance, an organization that could use this would be the African Physical Society, of course, and also like the African Materials Research Society could have a presence here, and it could be for that organization a way to organize a community of synchrotron light sources amongst AMRS members. And those individuals would be in the database with other light source users from around the world and from other fields. So under science organizations, you could have Materials Research Society, you can have a Chemical Society, you can have even paleontology societies, which is material science to some people's mind. So this is the way. So this is sort of the categorization, taxonomy of partner types. I mentioned that each individual can have a blog, and there will be this is the page of the blog network. So I put there's some test blogs here, but this is a blog article that I wrote several years ago. These are just some samples. But as you write your own blog, and actually writing your own blog is a great way to increase your citations. That's a well-known and very robust result in scientometrics. Is that if you write a blog about your work, you get more citations. I mentioned groups. So these are interest groups. So there's a group for accelerator components and systems. There's a group for user organizations, relationships. This is something we call the Light Source Facilities Planning Group. Africa and AOFSRR is the Asia Oceanic Forum for Synchrotron Radiation Research. So it is basically a users group for the synchrotrons in Asia, in East Asia. Now, so what's interesting about that, if you have this sort of group, one of those facilities is the Photon Factory in Japan. So the Photon Factory is basically looking forward to basically a complete upgrade. And we made these synchrotron facilities planning groups to get a space for collaboration for something like the African Light Source, which is thinking about a new build, and the AOF SSR, which is looking for like a major upgrade. So we think about the African Light Source being a new build in 10 years or so. And I would say also who's walking with us in this journey is like the Photon Factory, which more or less will be almost a completely new light source facility in 10 to 15 years, because they will have upgraded all their beam lines. And Tessima can explain, can attest to this. I mean, it might not just be upgrades; it might be like a complete decommissioning and scrapping, and using the space for something entirely new. So, what this collaboration space could hopefully facilitate is collaboration on the technical designing and planning for this. So there are a number of these synchrotron facilities planning groups, but there's also groups on specific topics. So here's a group we created on ARPS. So hopefully, we have this website with all these different users, hundreds or thousands of users, and then you have a group of them that they can join within the site for people who are ARPS people. The website also can be a portal for online courses. So that's a whole thing about how do you use your lecture notes and all of that you might use for in-person teaching. How do you configure that for an online course? And there's a We need a lot of that because in Africa, because we're trying to build capacity. And so online courses is kind of a quick way to do that. And these are just some courses that course names are sort of made up, even though there are actually some people working on some of these course titles. But it could be any course. This course actually exists. The Introduction to Synchrotron Radiation and Free Electron Lasers. That's a real course that you can go to on edX. But you can see we can make courses of any topic. And it's part of teaching training these days to figure out, how do you make your course into a massively online course. So to summarize what this is all about is that individuals, so you can use this website, which is, again, I give you the generic URL, lightsourceusers.org. You can engage the site as an individual. You can engage the site as a facility. You can engage as a beamline, and on down to the types of partners, centers, agencies, universities, science organizations. What's particularly relevant here is the professional associations and also the individual facility users group. What's important is that we can make the site responsive to multiple domain names. So let's say if you're the African Materials Research Society and you want a portal, but you want to use your domain name. So I don't know what it is. Let's say African Materials Research Society.org. We can facilitate that such that you have your own customized landing page so that for your members, it looks like something that your organization created. But and you could say you did, but it's a facility that your members can use to network with people in the synchrotron light source world. So think of this website as a global users facility. Then you can use it to learn, you can use it to teach, you can grow your organization, grow your network, collaborate, and all in a cycle where the whole world sort of, or at least our world, grows. So the open discussion thing that I wanted to ask is two basic questions. Is, would you use such a site? And what features would be important to you if you did want to use the site? So that's the last of my presentation, and I open the floor for discussion. Any questions? Did I lose everybody?
It's a very nice
Yeah.
website. I just clicked on it and browsed it directly, and beautifully done, very comprehensive.
Yeah.
But do you have would you how would you pay for all of this? Is that a membership fee, or how does it work?
Yeah, so right now we have a little bit of external funding. At least I have some external funding for it, and we would hope that there would be some partners that can help, sustain it, because the server space. So you can't put a site like this on a normal server. It takes a very specialized server. And so right now we have a contract, for a period of time for the server space, but it's not cheap. I mean, it's not a normal server. It is actually customized for this type of thing. So it's very resource intensive. And you couldn't even put it on like a scientific supercomputing center. I mean, it takes a very specialized configuration.
Who was seeding this? Which was funding? Who was giving you the seed funding? Or you don't want to disclose?
Yeah, I think the donor wants to remain anonymous, to tell you the truth.
Okay. Because it's not on the website, that's right.
No, that's not, the donor will not ever disclose themselves, I think.
Okay.
But I think, so one of the things that we're sort of looking at, and you can imagine, you have, let's say, each facility of the 40, 50 of them, and their user organization sort of joins this site, right? So now you have like thousands of individuals. Think of it as a LinkedIn or Facebook for LightSource users. But that's in the social networking, social media business, that's the product is the network. So the people who own social networking sites don't think of you as a customer, they think of you as the product. So, and that's one of the reasons why, you have to have, if you are interested in this type of thing, you want to create your own social network. So that way you get to make the rules, and, you get to set the standards, and you get to decide what the features are and all of that. But also, what if there became sort of a international society of LightSource users, right? And then that would be very good for the LightSource community, because there would be more collaboration in designing, beam time proposal preparation. And you can think of a sort of an international union of LightSource users, just like there's the International Union for Materials Research Societies. So
LightSource, have you pitched this to lightsource.org themselves?
Yes, I have. So the lightsources.org, that's out of Diamond. And that what they are mostly a communications and public relations group. That's the people who are behind, who work that site. That's what they do mostly. So they're more about, creating publicity, not publicity for the facilities, for external communities or external audiences. But also, you get the lightsources.org newsletter, right? So that's also has an internal audience component, and internal to LightSource users. Right, because you get the newsletter, you get a little snippet of what research is happening. But that is at the level of I guess it's intended for external audiences, so not necessarily users themselves. But let me respond to this thing in the chat. Someone put in create a journal on the AfLS platform, and that way you can publish editorials, comments, and interviews. Okay, so I get the point, and I understand where you're going there. A journal itself is that's going to be hard, and actually probably impossible. Journals take a lot of capital, a lot of money up front, and they take a lot of money up front, in the middle, and in the end. And then because the LightSource users are varied, right? So, and they probably need to publish in the primary journals in their particular fields. So a single LightSource journal that covers, all beamlines, all techniques, all types of users is close to impossible. The closest one is maybe the journal Synchrotron Radiation. But, that one exists, and it would be difficult to sort of compete against that well-established journal. There's also Synchrotron Radiation News, which is sort of a more of a quarterly magazine that may have like research summary articles from time to time. But what we have thought about is an African light source preprint server. So now that allows people to to upload their preprints. Now, so the difference between a preprint server and a full-fledged journal is the preprint server where you don't do all that peer reviewing and typesetting, which is the entirety of that process is what adds cost. So so you go to a journal and they want to charge a page charge of say $300 per paper. Well, that's what that pays for. The peer reviewing, everything that's involved from submission to production to sales and fulfillment comes out to about $300 a paper. And unless you're willing to pay, unless you have people who are willing and capable of paying those page charges, or you have some kind of mechanism to cover that cost, then a journal, a sustainable journal, is close to impossible. But if you have a preprint server, a lot of that cost goes away. It doesn't go to zero, but it goes to something that maybe we can manage. So look for that in 2026. Now, what's also important for the African light source and all these other facilities is it's an important aggregator. So it's important. It would be important to us, for instance, to know what are people publishing? What are Africans publishing in the synchrotron light source realm, right? And they could be publishing. I mean, that would be hard to aggregate, right? Because it could be everything from anatomy and archaeology to virology and zoology. So no one can read all those journals and keep up with all those different fields. But if we got people into the habit of at least posting their article on a preprint server, and it's a well-known result that if you use a preprint server like Archive, then you get more citations. That's a very robust result. Essentially, the more you make your work available in other types of forums, so preprint servers and blogs, the more attention it gets and the more citations you get. So that is that's a sort of making that preprint server is a different project from this website, but related. Any other questions? Comments? So, Abram, are you still here? Is that you?
Yes, that's me. Yes.
Yeah, you haven't said anything.
Yeah, I just asked if the person that's seeding the development of the platform, is it a free will donation or are they viewing it as a contribution for an investment?
I think we have not had that conversation with them. We'll have to we'll have to see. Because the people there are people who are in the sort of social networking business who, I mean, when you're into that, the network itself, the individuals in the network, they're not customers, they're the product, right? So you can imagine, a donor that's like a company, and I mean, just say company that sells detectors, right? They would love to be able to be the first company that comes to mind when you are trying to buy a detector, right? I would love it if their company was synonymous with I need a I want to buy a detector. Just like well, you know, Escalator. Escalator was the name of the company that first made what we call escalators. And no one says movable staircase. Everyone says escalator.
Yeah, I mean, there are a number of ways I think that such a venture could be monetized, you
Yeah.
know, and I guess the concern would be that ultimately that the investors' objectives are not counter to the goals and out of alignment with the goals of AfLS. I mean, I think that this kind of platform has a lot of merits from the standpoint of collaboration, different user groups at different light sources. You know, I think that it provides opportunity to facilitate the connections, and that's great. And I think there's a lot of opportunity for advertisement as well. I wonder about this type of platform serving, you know, the benefit of AfLS through some.
Oh, you broke off there. But yeah, I mean, I will say that I mean, sponsor management is always an issue, right? Be it a government or whomever.
Yeah, and I think that this could be an opportunity to consider ways in which this could be of use and service to AfLS from
Yeah.
a funding standpoint. Yeah, that's just my thoughts.
Okay. Philip, are you there? I think I may have lost everyone to the end of the day, right?
Lawrence, are you
Yes.
talking to me?
Yes. I was wondering if you had any comments on the presentation.
Yeah, it was great. I think we can. My worry just is how we can be able to manage it. How we
Yeah.
can be able. Yeah, that is just my only point of view. Because if you want something like it's a global stuff, which
Right.
require different session for different world which to be participated. Maybe we might have like a committee or something, or they discuss it in different user meetings so that they can
Right.
be able to update the system. That's another way that we can be able to populate that website.
Yeah, and that's so there's there's a sort of the technical management of the site. So just making sure that the servers are well maintained, that the software is upgraded appropriately, and we have a team of developers who handle that. And the software runs on a very, very specialized server environment, to the point where the company that offers the server environment, that's all they do is run this particular software. So which is good and bad. Actually, we have a no, I have a hot version, a warm version, and a cold version. So in software talk, so the hot version is the one that's working, that your users can that they go to. That's the one that's working production. The warm version is the one that you keep warm just in case the hot server goes down for any particular reason. So there could be a power failure or power glitch at the warm server farm, and there's a way for to automatically switch over to the warm server. And then when the warm server, when the hot server comes back up, it switches back. And that's commonly done. The what it requires is a lot of server to server communication, because you want the hot server and the warm server to always have the same content and everything. So there's a sort of a frequency at which the hot and warm server sort of communicates with one another. And I have to say that that is actually being done less and less now, because people are feeling like the server machines themselves and the server farms that house them are becoming reliable enough. And then there's the sort of cloud computing that you don't need that secondary setup. So a lot of people are abandoning the warm server. And then the cold server is, just in case lightning strikes everything, at least you have your one last good copy of the site that you can say would probably take you a few hours to bring back online, just in case something happened to everything and everybody. And then besides that there's the developer copy. So that's the one that the developers are always using and testing. And that one is generally not available to the public. It's only available to the developers. So you need all of that. And you need a bunch of other stuff too. Professor Wege, have you been listening to this? Yeah, maybe not. No.
What's the Loris?
I wondered, have you been listening to the presentation, and what are your thoughts?
Yes, it was a very, very good presentation with a lot of information. Thank you very much. It was great.
So let me go ahead.
Yeah?
Go ahead. Go ahead. So let me just actually tell you just quickly. I mentioned that professional associations can have their own portal. I believe if you go to, or matter of fact, I know, go to Baryons, so BARYONS .africanphysicalsociety.org, and you'll see a page like this.
Okay, thank you. It's good to know that.
Can you post that in chat, Loris?
So let me put Baryons African Physical Society.org. And let me show you another one just to sort of give you a sense of I think it's battery research.org. So I think, if you had it might be batteries research, but let me check. But you can imagine like a sort of an African batteries research hub. So tomorrow at noon GMT, we're going to hear a talk from the European Batteries Hub, right? And one of the plans, or a plan, is to create a African batteries research. So this is the European Batteries Hub. And it's African battery research. I mean, it would be great to have a African batteries research hub. And there are batteries research groups in in Africa. There's actually, I guess Japan is setting up a center, what they call a center of excellence at one of their universities in the Democratic Republic of Congo. And I guess who's behind it is what's the guy that won a Nobel Prize for inventing the lithium-ion battery? I guess the government of DRC was able to get that center in Japan to invest into this center of excellence in DRC. So there's a lot of different configurations in which, you know, different organizations, different facilities, academic departments can participate in the site. Any other questions? Well, if there's nothing else, I get to let you guys sort of chew on this website idea. And if you have any questions, you can always just contact me. Let me put my email in the chat. And you can contact me with ideas on what the site can include, should include, and how it should be managed. Okay.
Okay, thank you very much.
Okay. All right.
Nice. Great talk.
Yeah, we talk later. Yeah.
Yep. Okay, we'll do.
This is the end of the session today?
This is the end of the session today.
Okay. Lawrence, tell me, don't forget to find a window for this professor from Senegal tomorrow morning.
He should just come to the conference, because there's always someone who doesn't show up.
It is Biran. He say he can talk tomorrow morning.
Yes.
You got his mail?
I do.
Okay, thank you.
Okay.
Yeah. Once I receive the abstract from Aru, I will send it to you.
Okay. Yeah. Right. I very, very much need that. Okay. All right. I will see everyone tomorrow.
Okay. Thank you. Bye bye.
Okay. Bye bye.